In this presentation we introduce the concept of electric field describing electrostatic interactions between charges or charged bodies. Since we focus on time-independent electrostatic interactions, we can use the term electrostatic field. We will define electric field strength, which gives a quantitative description of electric fields based on the application of Coulomb's law. We also demonstrate that the principle of superposition holds for electric fields. We will introduce electric field lines providing a visual representation of the geometry that is the spatial distribution of electric fields. Then we determine the electrostatic fields due to point charges, dipoles and continuous distributions of charge, such as a uniformly charged line and a uniformly charged plane by applying Coulomb's law. We will also calculate the field strength along the axis of a uniformly charged circle and a uniformly charged disk. We also examine the motion of charged particles and dipoles in electric fields by applying the laws of motion for the electrostatic force, and determine the equations of motion of electrons propagating in a uniform electric field. We will see that an electron can move as free-falling particle or a horizontal projectile in the field, depending on its initial velocity. Then we present Millikan's oil drop experiment in which the charge of oil droplets was measured in a uniform electric field, and the elementary electric charge was determined from the results of the measurement. We will also define electric flux and determine the electric flux through a closed surface for a point charge. We generalize this result for an arbitrary distribution of charge and prove Gauss's law. The law establishes a relationship between the electric flux through a closed surface and the amount of electric charge enclosed by the surface. We derive the law in differential form, where the divergence of the electric field measures the intensity of the source charge of the field. We will finish this presentation with the application of Gauss's law and the principle of superposition of electric fields to determine the electric field due to symmetric charge distributions, such as a point charge and a uniformly charged line or plane. We will see that this method simplifies the computation of the field in a great extent, and also allows us to derive the electric field produced by a uniformly charged spherical shell or sphere. We are already familiar with the notion of electric charge used to model electric phenomena. We can extend this description of electricity by introducing the concept of electric field. We saw that Coulomb's law determines the force acting between 2 point-like static charges, but it does not explain what is the mechanism conveying force between two charged bodies which are separated in space. Historically, action at a distance was one of the possible explanations of this phenomenon, stating that the force is exerted on a body instantaneously by another one without any intervening medium. This theory was applied for both gravitational force and electrostatic force. However, the results of the experiments studying the propagation of electromagnetic waves contradicted the theory of action at a distance. Faraday provided another explanation for the presence of a force between charged bodies. He suggested that an electrically charged body creates an electric field in its vicinity, and this field transforms the geometric space around the charged body to a physical space. For example, let us consider a point charge Q1 which creates an electric field around itself. If a point charge Q2 is brought into the electric field created by the charge Q1, then a force will be exerted on the charge Q2 by this field. That is, the charge Q1 has an effect on the charge Q2 through its electric field. Since the charges Q1 and Q2 are opposite charges, the charge Q1 will attract the charge Q2. But Newton's third law states that every action in nature has an equal and opposite reaction. Therefore the electric field created by the point charge Q2 exerts the same amount of force on the charge Q1 pointing in the opposite direction. That is, the charge Q2 will also attract the charge Q1 with the same force. Generally, if point charges are placed in each other's electric fields, then these fields are the mediators of the interactions between them. It follows from the above considerations that the relationship between electric charge and electric field is twofold. On the one hand, an electric charge creates an electric field, that is, charge is the source of the field. On the other hand, the electric field has an effect on the electric charges placed in the field. Therefore we have to solve two different problems. The first problem is to give a quantitative description of the electric field created by a given distribution of electric charges. The second problem is to determine the forces acting on electric charges placed in a given electric field. In order to determine the electrostatic field created by an electric charge at rest, we handle the charge Q creating the electric field separately from the charge QP probing or testing the electric field. We call the charge QP test charge and use the subscript P for probe to avoid the usage of the letter T, which normally indicates time dependency. The test charge must be a point charge, That is, it must have a negligible size and volume with respect to the characteristic length scale of the electric field. It is an important requirement, so that we can probe the local properties of the electric field in the point of the test charge instead of measuring the average effects of the field over a greater spatial volume. Here we illustrate this criterion with the inequality stating that the size of the test charge, approximated with a sphere of a diameter of d, is much smaller than the characteristic size L of the electric field. Another requirement for the test charge is that QP must have a negligible amount of charge, so that we could reduce the effect on the electric field due to its presence, which changes the distribution of the charges creating the electric field. This criterion tells us that the charge QP must be much smaller than the net charge Q in the system of charges. We will apply the method with test charges to study the electrostatic field created by a point charge Q. Let us place a series of test charges, denoted by QP1, QP2 and so on, in the position R1 with respect to a reference point O, and determine the electrostatic forces, denoted by F1, F2 and so on, exerted on the test charges by the charge Q. Here we have the point charge Q and we choose a reference point O, which fixes the frame of reference. Then we place the test charge QP1 in the position R1, where the position vector R1 points from the reference point O to the test charge. If we know the position vector O pointing from the charge Q to the test charge QP1, we can compute the force F1 acting on the test charge by applying Coulomb's law. Then we can replace the test charge QP1 with the test charge QP2 and compute the force F2 acting on the test charge. If we perform this procedure with each member of the series of test charges, we can compute the force exerted on each test charge, for example on the test charge QPI. As a result, we obtain a series of forces acting on the series of point charges. The experiments demonstrate the following relations. If we compute the ratio of the electrostatic force F1 to the test charge QP1, it will be equal to the ratio of the force F2 to the test charge QP2, and so on. That is, the ratio of any force Fi to the test charge QPI in the series is equal to all the other ratios calculated for the rest of test charges. Therefore, the ratios give a constant vector which we will denote by the letter E, indicating the term electric. This vector only depends on the position of the test charges but is independent of the test charges themselves. For an arbitrary test charge QP placed in the point R1, we can express the force F exerted on the test charge by the charge Q, as the product of the charge QP times the vector E computed in the point R1. We can repeat the experiment by moving the point charges to another position and calculate the forces acting on them. Let us move the series of point charges QP1, QP2 and so on to the point R2, where the position vector R2 points from the reference point O to the new location, and determine the forces F1, F2 and so on in the position R2. The experiment demonstrates that the ratios of the force Fi to the test charge QPI will be equal to each other for all the index I. That is, the ratios are equal to the same vector E determined in the point R2. The vector E is constant for each test charge, and only depends on the location of the test charges determined by the position vector R2. For an arbitrary test charge QP, we can write that the force F acting on the test charge in the point R2 is equal to QP times the vector E determined in the point R2. If we perform this experiment in many points R1, R2, R3 and so on in the vicinity of the point charge Q, then we will obtain the same result. In general, the force F acting at test charge QP in the point defined by the position vector R is always equal to QP times the vector E determined in the position of the test charge. That is, the electrostatic force is proportional to the amount of the charge QP, where the proportionality factor is the vector E. We also see that the proportionality factor E only depends on the position R. Therefore we can associate a vector-valued function ER with each point R in the vicinity of the point charge Q, and determine its value by measuring the force acting on the test charge QP. We interpret this vector-valued function as a quantity describing the electric field around the charge Q. We call the vector-valued function E electric field strength, which assigns the vector E to each point in the space. If the electric field strength is known, then the force acting on the test charge QP can be determined without applying Coulomb's law. The electric field cannot be seen or perceived, but it is present everywhere around charges, and responsible for the electrostatic interaction between charged bodies. That is, the electric field strength represents the same physical reality as the bodies which we can see and perceive. We can express the electric field strength at a given position in the vicinity of its source charge as the ratio of the Coulomb force measured at the position to the test charge QP applied in the measurement. We see from this equation that the unit of the electric field strength is equal to Newton per Coulomb. The electric field strength is unity in a given point, if 1 Newton force acts on 1 Coulomb charge in that point. By virtue of this formula, we can state that the electric field strength in a given point is equal to the force acting on a unit positive point charge located in the same point. The direction of the vector-valued function E is the same as the direction of the force acting on the unit positive point charge. If we use a negative point charge, the direction of the field strength will be the opposite to the direction of the force. In many cases we just use the term electric field E instead of the electric field strength when we talk about the vector-valued function E describing the electric field in every point of the space. If the direction of the electric field strength is independent from the position, that is the vector E is constant, then we call it a homogeneous electric field. Otherwise we talk about an inhomogeneous field, and the vector-valued function E determines the variation of the electric field strength in space. We have already applied the principle of superposition for the Coulomb forces acting in a system of point charges. Since the electric field strength is determined by Coulomb's law, we can extend this principle to the electric fields created by a system of point charges. We can state that the net electric field strength of a system of n point charges in a given point is the vector sum of the electric fields E1, E2, ellipsis, En produced in that point by the individual charges in the system. In order to describe the electric field around a point charge or charged body, we introduce the graphical representation of the electric field strength. We have seen that the electric field strength E is a vector-valued function mapping each space point into a vector. Therefore, the electric field E can be represented by an arrow in each point of the field, where the arrow points in the direction of the vector E in a given point, and the length of the arrow indicates the magnitude of the vector E in that point. However, such a representation is not convenient if we want to give a detailed description of the spatial distribution of the electric field. A possible solution to this problem is to represent the electric field by electric field lines or simply field lines. In this graphical representation, the relationship between the field lines and the electric field is the following. The tangent to a field line in any point gives the direction of the electric field E in that point, and the number of the field lines crossing the unit area element perpendicular to them at any point is proportional to the magnitude of the vector E in that point. The orientation of the field lines is indicated by short arrows drawn on the field lines in few points. The graphical representation can also visualize the magnitude of the vector E in a given point by the density of the field lines in the vicinity of that point, which is proportional to the field strength there. The denser the field lines are over an area in the graph, the stronger the magnitude of the electric field is in the space represented by that area. Now we can depict the electric field lines in the vicinity of different distributions of point charges, or charged bodies approximated by point charges. We start with the simplest example which shows the electric field lines of a point charge or a small charged sphere. Here we can see the field lines around a positive charge and a negative charge. In both cases, the field lines have a radial distribution due to the spherical symmetry of the source of the electric field. For positive charge shown in the left-hand side figure, the field lines are directed outward, which indicates the repulsive force acting on any positive test charge placed near the positive source charge. In the right-hand side figure, the field lines are directed inward, since the negative source charge attracts any positive test charge in its vicinity. The figures also show that the density of the field lines, representing the magnitude of the electric field, decreases with the distance from the source. In the next example, we will study the field lines around two equal but opposite point charges and two equal like point charges. Here we can see the field lines of a positive and a negative charge placed near each other, and here we depict the field lines of two positive charges with the same separation. For opposite charges, the field lines are directed from the positive charge to the negative one, as shown in the left-hand side figure. For like charges, the field lines are directed from the charges and diverge from each other, which we can see in the right-hand side figure. The topology of the electric field lines for two-point charges is more complicated than the one obtained for a single-point charge. In order to draw such a figure, we need to determine the electric field in every point around the point charges and construct the field lines from the direction and the magnitude of the net electric field strength. For a system of charges, we need to use the superposition principle to calculate the net electric field around the system, and then draw the field lines representing the field. In the general case, this is a difficult task. The next example is the visualization of the electric field around charged surfaces, where we depict the electric field line in the vicinity of opposite charges on two plane parallel plates. The photo shows an apparatus with two plates separated by a distance which can be adjusted by turning a screw. This is the cross-sectional view of the two identical plates, where the plate in the left-hand side attained positive charge and the one in the right-hand side has negative charge. The charges are evenly distributed throughout the plates. Since the geometry of the apparatus is symmetric, the electric field lines have also a symmetric distribution around the plates. All the field lines are oriented from the positively charged plate from the negatively charged one. We also see that there is a region between the plates, where the field lines are only slightly bent and almost parallel to each other. If we reduce the distance d between the plates so that it becomes small enough with respect to the linear size L of the plates, then the field lines become parallel to each other and evenly distributed. That is, the electric field strength has the same magnitude and points in the same direction in the whole space between the plates. As a result, we created a uniform or homogeneous electric field between the plates, which are the basic idea of capacitors, as will be discussed in more detail later. In a simple experiment, the electric field lines can also be demonstrated with the distribution of grass seeds floating on castor or mineral oil, if the grass seeds are exposed to a strong electric field. In the first example, we can study the field lines around a point charge. Here a small container is almost completely filled with castor or mineral oil and grass seeds. We connect the metal ring in the figure, or the container in the photo, to the ground, and charge the metal cylinder placed in the middle of the container. Then the electric field created by the charged cylinder polarizes the grass seeds, aligning them in the direction of the electric field lines. In the photo we can see the radially symmetric distribution of the seeds around the charged cylinder, called electrode. In general, an electrode is a conductor which carries electric charge into nonmetallic materials. Here the cylinder and the ring in the figure, or the container in the photo, work as electrodes. In the second example we demonstrate the electric field lines in the vicinity of a pair of opposite charges. Here two metal cylinders are immersed in the oil and charged with opposite charges. The electric field created round the electrodes produces electric field lines connecting them. In the photo the polarized grass seeds are aligned in the direction of the bent electric field lines, which have a symmetric distribution. In the last example we show how to reproduce the cross-sectional distribution of the electric field lines between two plain parallel plates with opposite charges. We can use two metal wires or narrow metal plates as electrodes. If the wires or the plates are immersed in the oil and attain opposite charges, then the electric field aligns the seeds in the direction of the field lines between them. In the photo we can see the grass seeds are arranged in chains along the field lines connecting the electrodes, and these chains are more or less parallel to each other. In the following examples we determine the electric field around different source charges by applying Coulomb's law. We start with the simplest example, where we compute the electric field created by a point charge Q in a given point P, which is in the vicinity of the source charge. For a given reference point O, the position vector of the point charge is denoted by R0 and the position vector P determines the point P. The vector R is the difference of the position vectors, and its length is equal to the distance between the point charge and the point P. If we place a test charge QP at the point P, then we can use Coulomb's law to describe the electrostatic force exerted on the test charge by the source charge. Here the charges are like charges and the point charge Q repels the test charge. We know that the electric field strength E in the point P is given by the force F acting on the test charge divided by QP, the amount of test charge. Coulomb's law tells us that the force F is given by 1/4 pi times epsilon naught, times the ratio of Q times QP to the square of the distance R between the charges, times the unit vector pointing from the source charge to the test charge. Since we see QP in both the numerator and the denominator of the fraction in the right-hand side, we can drop QP. As a result, we obtain the electric field E in the point determined by the vector R, which is equal to 1/4 pi epsilon naught, times the ratio of the charge Q to the square of the length of R, times the vector R divided by its length. This formula shows what we expected. The distribution of the electric field is spherically symmetric around the charge Q, and the electric field strength E points radially outward from the source charge. The magnitude of the vector E is inversely proportional to the square of the distance from the charge. We can also express this formula in the terms of the position vectors of the charge Q and the point P. Now we can determine the electric field strength everywhere around the charge Q. For example, if the source charge is equal to 1 Coulomb, then the field strength in the distance of 1 meter from the charge is equal to 9 times 10 to 9 Newton per Coulomb. This result simply follows from the fact that the multiplicative factor 1/4 pi times epsilon naught is equal to 9 times 10 to 9 Newton meter squared per Coulomb squared. We have seen that the electric field strength around the point charge q is inversely proportional to the square of the distance from the charge. Then we can specify the number of the field lines originating from the charge plus q or terminating at the charge minus q. This is equivalent to the specification of the density of the field lines, which can be defined as the number of the field lines passing through an area perpendicular to the field lines divided by the area. Now we accept the following convention. We draw the field lines in each point of the space such that the density of the electric field lines in a point gives the magnitude of the electric field strength E in that point. That is, the number of the field lines passing through a unit area perpendicular to the field lines gives the magnitude of the electric field strength E at the unit area. This relationship between the density of the field lines and the electric field strength is obviously a local definition. For inhomogeneous electric fields, the infinitesimal unit area element provides the local value of the field strength. If the spatial distribution of the electric field exhibits some symmetry, then we can also use a surface over which the magnitude of the field strength is constant. We count the field lines passing through the surface, and divide the result by the area of the surface. The spherically symmetric electric field around the point charge q is a good example for the latter case, where the magnitude of the electric field strength follows the inverse square law, and it is constant over any sphere with a point charge in its center. Let us enclose the charge q with such a sphere with an arbitrary radius r, where the surface area as of the sphere is given by 4 pi times r squared. All the electric field lines originating from a positive charge or terminating at a -1 will cross the sphere. Then we obtain the number of the field lines passing through the sphere, if we multiply the density of the field lines on the spherical surface by the area of the sphere. It follows from our convention that the density of the field lines is simply the magnitude E of the electric field strength, whereas the area of the sphere is given by as. For the point charge q, this gives q divided by 4 pi times epsilon naught times r squared, times the area 4 pi r squared. We can reduce this expression to q divided by epsilon naught. Then we state the following. The number of the field lines originating from a positive charge q, or terminating at a negative charge q, is equal to the amount of charge q divided by the vacuum permittivity epsilon naught. We have already explained that the principle of superposition can be applied for a set of electric fields produced by a system of point charges. Now we can see that the net electric field created by the point charges q1, q2, qn and an arbitrary point p is given by 1 over 4 pi times epsilon naught, times the sum of the ratio of qi to ri squared, times the vector ri divided by the length of ri, for the index I from 1 to n. Here the vectors ri point from the point charge qi to the point p. In the sum, each point charge appears with a weighting factor, which is proportional to its amount of charge and inversely proportional to the square of its distance from the point p. In the next example we will study the electric field around an electric dipole. An electric dipole is defined as a couple of equal but opposite point charges plus q and minus q separated by a distance d. By default, the direction of electric dipoles determined by the vector d is always from the negative charge to the positive one. The midpoint between the positive and negative charges is called the center of the dipole. We introduce the electric dipole moment p of a dipole as the product of the charge q and the vector d. The SI unit of the dipole moment is Coulomb meter. This quantity is not unique in the sense that the dipole moment does not change if we modify the charge q and then the distance d such that their product remains the same. However, we will see that the dipole moment arises in a natural way in the description of the electric field around a dipole. We have already seen the electric field lines of two opposite charges places near each other, where the field lines are directed from the positive charge to the negative one. The figure shows that the topology of the electric field, that is the structure or the distribution of its field line around a dipole, exhibits a rotational symmetry around the axis of the dipole, and a reflection symmetry about its equatorial or transversal plane. If we change the charges plus q and minus q by the same amount, we do not break the symmetry of the field geometry. We change the magnitude of the electric field strength around the dipole, but its direction remains the same everywhere. As a result, the geometry of the field lines remains the same, that is, the field lines still have the same distribution. By changing the magnitude of the electric field, we modify the density of the field lines, whereas their geometry describing the direction of the electric field does not change at all. The figure shows that the density of the electric field lines around a dipole with the charges 2 times plus q and minus q is greater than the one for the dipole with the charges plus q and minus q. Then the number of the field lines passing through a unit area perpendicular to the field lines gives a greater magnitude of the electric field everywhere around the dipole. Since the electric dipole is a simple system of point charges, we can apply the principle of superposition for electric fields. This tells us that the electric field strength of a dipole is the vector sum of the electric fields of the positive and the negative charges of the dipole. First, we study the electric field of a dipole at special locations, such as on the axis and the equatorial plane of the dipole. Then we will determine the electric field in an arbitrary point in the vicinity of the dipole. In the first case, we determine the electric field of the dipole along its axis, that is in a point P on its axis at the distance r from the center. In the point P, the electric fields E sub plus and E sub minus created by the charges plus Q and minus Q are parallel with the axis, but E sub plus points outward and E sub minus points inward. The distances of the point P from the charges plus Q and minus Q are given r minus d over 2 and r plus d over 2, respectively. Then the magnitude of the electric field E sub plus in the point P is equal to 1 over 4 pi times epsilon naught, times the charge Q divided by the square of r minus d over 2, whereas the magnitude of the electric field E sub minus is equal to 1 over 4 pi times epsilon naught, times the charge Q divided by the square of r plus d over 2. Since the point P is closer to the positive point charge than to the negative one, the electric field E sub plus is stronger in that point than the electric field E sub minus. By applying the principle of superposition of electric fields, the net electric field can be written as the vector sum of the electric fields. Since these fields are parallel with each other but have opposite directions in the point P, the net electric field E points in the direction of the field E sub plus. Then the magnitude of the vector field E of the dipole is given by the difference of the magnitudes of E sub plus and E sub minus, and we obtain Q divided by 4 pi time epsilon naught, times 1 divided by the square of r minus d over 2, minus 1 divided by the square of r plus d over 2. We can rename the fractions in the bracket with a common denominator, and subtract them, which gives the square of r plus d over 2 minus the square of r minus d over 2, divided by the square of r minus d over 2 times the square of r plus d over 2. After simplifying this expression, we obtain 2 times r time d divided by the square of r squared minus d squared over 4. If the spatial extension of the dipole is negligible with respect to the distance of the point P from the center, that is d is much smaller than r, we can approximate this result as the ratio of 2 times d to the cube of r. Then the magnitude of the electric field of the dipole is equal to Q divided by 4 pi times epsilon naught, times the ratio of 2 times d to r cubed. Since the dipole moment P is defined by the charge Q times the vector d, the electric field E of the dipole in an arbitrary point along the axis is given by 1 over 4 pi times epsilon naught, times 2 times the dipole moment P divided by the cube of the distance r of the point from the center. We see that the electric field points in the direction of the vector d along the axis. This is also the case for the point P placed in the left-hand side of the dipole. Since the electric field E sub minus is stronger there than the electric field E sub plus and it points inward the center, the vector sum of the two electric fields still points in the direction of the vector d. In the second special case we study the electric field of a dipole with the charges plus q and minus q separated with the distance d in the equatorial plane of the dipole, which is perpendicular to its axis and crosses it at the center. Any point P on the equatorial plane at a distance r from the center has the same distance from the positive and the negative charges, which is equal to the square root of r squared plus the square of d over 2. Then the magnitudes of the electric fields E sub plus and E sub minus are also the same in that point, which are equal to 1 over 4 pi times epsilon naught, times q divided by r squared plus the square of d over 2. We can apply the superposition principle again and use the parallelogram law to construct the electric field strength E of the dipole in the point P. By virtue of the symmetry of the parallelogram spanned by the vectors E sub plus and E sub minus, the orthogonal projections of the vectors on the equatorial plane cancel each other out. At the same time, their orthogonal projections on the axis can be summed up, which are equal to the magnitude of E sub plus times cosine theta and the magnitude of E sub minus times cosine theta. Since the magnitudes of E sub plus and E sub minus are the same in the point P, the electric field E is equal to 2 times E sub plus times cosine theta. Here cosine theta can be expressed by the ratio of d over 2 to the square root of r squared times the square of d over 2. Now we can write that the magnitude of the vector E is equal to 2 over 4 pi times epsilon naught, times q over r squared plus the square of d over 2, times d over 2 to the square root of r squared times the square of d over 2. Then we obtain q over 4 pi times epsilon, times d over 2 divided by the r squared plus the square of d over 2 to the power of 3 over 2. If we assume that the distance r of the point P from the center of the dipole is much greater than the distance d, we can approximate the fraction with the ratio of d to r cubed. Then the electric field can be written as q over 4 pi times epsilon naught, times d over r cubed. Since the dipole moment P is equal to q times d, the electric field E of the dipole in any point on the equatorial plane of the dipole is equal to minus 1 over 4 pi times epsilon naught, times the dipole moment P divided the cube of the distance r of the point from the center. The minus sign in the right-hand side of the formula indicates that the electric field in the equatorial plane and the dipole moment have opposite directions, as seen in the figure. After having determined the electric field of a dipole in special cases, let us study the general case, and calculate the electric field of a dipole with the point charges plus q and minus q in an arbitrary point P. We assume that the distance d of the charges from each other is much smaller than their distances from the point P, which are equal to the lengths of the vectors r sub plus and r sub minus, pointing from the charges to the point P. That is, the length of the vector d is much smaller than the lengths of the vectors r sub plus and r sub minus. If we apply the principle of superposition for the electric fields E sub plus and E sub minus created by the point charges plus q and minus q, we can write that the electric field E around the dipole is equal to the vector sum of E sub plus and E sub minus. Now we substitute the result obtained for a single point charge into this equation, which gives 1 over 4 pi times epsilon naught, times the ratio of the charge q to the square of the length of the vector r sub plus, times the vector r sub plus divided by its length, minus 4 pi times epsilon naught, times the ratio of the charge q to the square of the length of the vector r sub minus, times the vector r sub minus divided by the square of its length. Then we have q over 4 pi times epsilon naught, times the vector r sub plus divided by r sub plus cubed, minus the vector r sub minus divided by r sub minus cubed. Our aim is to express the distances in this formula in the terms of the distance r of the point P from the center of the dipole. If the vector r points for the center to the point P, then the vector r sub plus can be written as the vector r minus 1 over 2 times the vector d. Similarly, the vector r sub minus will be the vector sum of the vector r and 1 over times the vector d. If the angle between the vector d and the vector r is denoted by theta, we can apply the cosine theorem to express the squares of r sub plus and r sub minus as the square of r, plus the square of d divided by 2, minus or plus 2 times d divided by 2 times r times cosine theta. We can factor r squared out and we obtain r squared times 1 plus the ratio of d squared over 4 minus or plus d times r times cosine theta to r squared. Now we can write that r sub plus or minus to minus 3 is equal to r to minus 3, times a factor to minus 3 over 2, where the factor is given by 1 plus the ratio of d squared over 4 minus or plus the scalar product of the vectors d and r to r squared. The right-hand side can be written as r to minus 3, times 1 plus x to minus 3 over 2, where x is defined by the ratio of d squared over 4 minus or plus the scalar product of the vectors d and r to r squared. We have assumed that the size of the dipole is negligible with respect to the distance between the dipole and the point P, and the length of the vector d is negligible to the length of the vector r. Therefore x is small, and we can use the Taylor expansion of the function 1 plus x to n, which is 1 plus n times x, plus n times n minus 1 over 2 times x squared and so on to approximate the result. Then r sub plus or minus to minus 3 has the first order approximation of r to minus 3, times 1 minus 3 over 2, times the ratio of d squared over 4 minus plus the scalar product of d and r to r squared. Now we can write the electric field E of the dipole as q divided by 4 pi times epsilon naught, times the vector r sub minus the vector d divided by 2 over r sub plus cubed, minus the vector r sub plus the vector d divided by 2 over r sub minus cubed. If we reorder the terms, we obtain q times the vector r over 4 pi times epsilon naught, times r sub plus to minus 3 minus r sub minus to minus 3, minus q times the vector d times divided by 2 over 4 pi times epsilon naught, times r sub plus to minus 3 plus r sub minus to minus 3. The approximation of the first term in the right-hand side gives q times the vector r over 4 pi times epsilon naught, times the ratio of 3 times the dot product of the vectors d and r to 5. The approximation of the second term can be written as minus q times the vector d divided by 2 over 4 pi times epsilon naught, times 2 over r cubed, times 1 minus 3 over 2 times d squared divided by 4 over r squared. Let us inspect the second term. We see that the second term in the parentheses is proportional to d squared over r squared, which is negligible with respect to 1. Therefore we will keep only the first term in the parentheses and drop the second one. As a result, the approximation of the electric field created by a dipole is given by 1 over 4 pi times epsilon naught, times the ratio of 3 times the scalar product of the vectors p and r to 5, minus 1 over 4 pi times epsilon naught, times the vector p divided by r cube. Therefore, the electric field E created by a dipole with the dipole moment p in the position r is given by 1 over 4 pi times epsilon naught, times 3 times the scalar product of the dipole moment p and the position vector r times the vector r over r to 5, minus the dipole moment p over r cube. Since this formula is linear in the dipole moment p, which is proportional to the charge q, the electric field strength of the dipole is directly proportional to its charge. The formula also shows that the direction of the electric field remains the same in any given point if we change the charge of the dipole. That is, the density of the field lines depends on charge, and not their topology. We also regain the special cases from this formula. If the position vector points from the center to another point on the axis A of the dipole, then the dipole moment p is parallel with the position vector r. This fact allows us to write the dot product of the vectors p and r times the vector r as the dot product of the vector r with itself times the vector p. As a result, the first term in the square brackets is equal to 3 times the second one, which gives 1 over 4 pi epsilon naught, times 2 times the dipole moment p divided by the cube of the distance r from the center of the dipole. This is the formula which we derived for the electric field along the axis of a dipole with the dipole moment p. If the position vector points from the center to a point on the equatorial or transverse plane t of the dipole moment p is perpendicular to the position vector r. Then the dot product in the first terms in the square brackets vanishes and we have only the second term. That is, the electric field of the dipole is given by minus 1 over 4 pi epsilon naught, times the dipole moment p divided by the cube of the distance r from the center of the dipole, which is the expression we have obtained for the electric field in the equatorial plane of the dipole. From the general formula describing the electric field of the dipole we can determine the components of the electric field strength in a given point P, if we attach a Cartesian coordinate system to the dipole such that its origin is located at the center of the dipole and its x-axis points in the direction of the vector d. In this coordinate system, the components of the position vector pointing to the point P is given by the coordinates x and y, and the x component of the electric dipole moment is equal to P, which is q times d, while its y component vanishes. These vectors will be used to calculate the components Ex and Ey of the electric field strength of the dipole. The x component of the electric field strength can be written as 1 over 4 pi epsilon naught, times 3 times the dot product of the vectors p and r times x divided by r to 5, minus p divided by r cube. We can write the dot product of the vectors p and r as the product of their lengths times the cosine of the angle measured between them, and we can factor out p over r cube from the terms in the square brackets. Then we have 1 over 4 pi times epsilon naught, times p over r cube, times 3 times x times cosine theta divided by r, minus 1. Since x divided by r is equal to cosine theta, we obtain 1 over 4 pi times epsilon naught, times p over r cube, times 3 times the square of cosine theta, minus 1. The y component of the electric field strength is given by 1 over 4 pi times epsilon naught, times 3 times the dot product of the vectors p and r times y divided by r to 5. This expression can be written as 1 over 4 pi times epsilon naught, times 3p times y times cosine theta divided by r to 4. Since y divided by r is equal to sine theta, we obtain 1 over 4 pi times epsilon naught, times 3p times over r cube, times sine theta times cosine theta. The angular dependence of the components of the electric field strength clearly shows that the electric field is parallel with the axis of the dipole on the axis. Here theta is equal to 0 and cosine theta is equal to 1. As a result, the x component of the vector E is equal to the magnitude of the expression describing the field on the axis, while its y component vanishes since sine theta is equal to 0. In the equatorial plane of the dipole theta is equal to 90 degrees and cosine theta vanishes. Then the x component of E becomes negative, and its magnitude is given by the expression derived in the equatorial plane, while its y component still vanishes. That is, the electric field strength is also parallel with the axis or the dipole moment p in the equatorial plane but points in the opposite direction. We could use the components of the electric field strength to determine its magnitude in an arbitrary point, but we will apply the coordinate-free expression of the vector E of the dipole in the calculation. The square of the electric field strength E is proportional to 9 times the square of the dot product of the vectors p and r, times r squared over r to 10, minus 2 times 3 times the dot product of the vectors p and r times the dot product of the vectors r and p over r to 5, plus p squared over r to 6. This expression can be written as 3 times the square of the dot product of the vectors p and r divided by r to 8, plus p squared over r to 6. Since the dot product is equal p times r times cosine theta, we have 3 times p squared times the square of cosine theta over r to 6 plus p squared over r to 6. We can factor out the ratio of p squared to r to 6, and we obtain p squared over r to 6, times 3 times the square of cosine theta plus 1. Then the magnitude of the electric field of a dipole in an arbitrary point is given by 1 over 4 pi times epsilon naught, times the square root of 3 times the square of cosine theta plus 1. The formula shows that the magnitude of the electric field strength is inversely proportional to the cube of the distance from the center of the dipole, and it has an angular dependence. For a given distance from the center, the magnitude of the electric field reaches its maximum in the equatorial plane and it has a minimum value on the axis of the dipole. These formulas show that the electric field of a dipole falls faster than the one of a point charge, since 1 over r cubed is less than 1 over r squared for distances greater than 1 unit length. At small distances the electric field is dominated by whichever charges the point P is closer to, and the faster fall off of the field is the consequence of the fact that the electric fields of the charges almost cancel each other out for large distances. By applying Coulomb's law, we can also demonstrate that the electrostatic force acting between two dipoles parallel to each other is not a central force, and it is inversely proportional to the distance r between them raised to 4th power, provided the distance r is much greater than the distances between the charges in each dipole. Based on the superposition principle of electric fields, we can state that a system of point charges with zero net charge can be replaced by a dipole, where we place the sum of the positive and negative charges of the system in the two centers of positive and negative charges. For a given reference point O, the position of the point charge plus or minus qi in the system is given by the position vector r super plus sub I or r super minus sub I. Here we show the position vectors of the point charges plus q3 and minus q3. Then the centers of charges with respect to the reference point are determined by the sums of the distances of the point charges from the reference point weighted by the charges. The locations of the centers of the positive and negative charges are given by the position vectors r sub plus and r sub minus, which are equal to the sums of plus or minus q sub I, times the position vector super plus or minus sub I, divided by the sum of plus or minus q sub I for all the indices I. These vectors provide the position of the point charges of the dipole, and the sums of the positive and negative point charges in the system, denoted by plus or minus q, will be the point charges of the dipole replacing the system of point charges. If we place a body in an electric field, then Coulomb forces will act on the charge carriers and the basic constituents of the body. The electrons and the protons in atoms and molecules will be displaced with respect to each other by the electrostatic forces accelerating them in opposite directions. In insulators, this displacement separating the center of the charge for positive and negative charges is limited within the atoms and molecules. As a result, the atoms and molecules will become microscopic dipoles while the body remains electrically neutral. This process is called the polarization of matter. When we discuss the quantum nature of charge, we also mention that it does not play any role in the description of macroscopic charge attained by a body. Therefore, in the classical theory of electromagnetism we can apply the phenomenological description of charge, where the distribution of macroscopic charge in space is regarded as a continuous charge distribution. Such a continuous distribution of charge is described by the scalar-valued vector function called charge density. For a given point determined by a position vector r with respect to a reference point O, the charge density ρ gives the density of the charge in that point. However, the strict interpretation of the density of charge depends on the geometry of the charge distribution. If we consider a charge-thin wire, we study a one-dimensional problem, where the wire can be described by a space curve C. In this case the charge density describes the charge distribution along the wire, and the infinitesimal charge dq distributed along an infinitesimal length L of the wire is given by the charge density lambda times dl, where lambda is a function of the length L measured along the curve C. Here the charge density lambda along the curve C is defined by the derivative of the charge q with respect to the length L, measured from a given reference point on the curve. By virtue of this definition, the SI unit of the charge density is equal to Coulomb per meter. We can obtain the total charge q attained by the wire, if we integrate the charge density lambda along the curve C. Another typical problem in electromagnetism is the study of the charge distribution over the surface of bodies, the plates of capacitors, or interfaces between different materials. In such cases we apply a mathematical description of the surface S, and the charge density describes the charge distribution over the surface. The infinitesimal charge dq distributed over the infinitesimal surface or area element ds is given by the product of the charge density sigma and the surface element ds, where sigma depends on the coordinates u and v describing the position of the surface element on the surface S. As a result, we define the surface charge density sigma by the derivative of the charge q with respect to the surface area S, and the SI unit of the charge density is equal to Coulomb per square meter. In order to obtain the total charge q attained by a surface, an interface or a plate, we need to integrate the charge density sigma over the surface S. The most general problem considered in electrostatics is the study of charged bodies in the three-dimensional space. In such cases, we deal with charge distributed throughout the volume V of a body, and the spatial charge density ρ describes the charge distribution within this volume. Then the infinitesimal charge dq distributed in the infinitesimal volume element dV is given by the spatial charge density ρ times the volume element dV, where the charge density depends on the position vector or describing the position of the volume element with respect to a reference point O. As a result, we define the spatial charge density ρ by the derivative of the charge q with respect to the volume V, and the SI unit the spatial charge distribution is equal to Coulomb per cubic meter. The integral of the charge density ρ over the volume V gives the total charge distributed throughout this volume. If we want to determine the electric field in a given point P created by the macroscopic charge distribution Q, we can proceed as follows. First we apply the formula obtained for the electric field of a point charge to compute the contribution to the electric field in the point P from an infinitesimal charge in an arbitrary point within the macroscopic distribution of the charge. Then we integrate these contributions over the whole volume of the charge distribution, which provides the net electric field in the point P created by the total macroscopic charge. The electric field E of a point charge Q in the point P is equal to 1 over 4 pi times epsilon naught, times the charge Q divided by the square of the distance r between the point charge and the point P, times the position vector r pointing from the point charge to the point P divided by the distance r. If the source of the field is the infinitesimal charge dq approximated by a point charge, then its contribution dE to the electric field in the point P is given by 1 over 4 pi times epsilon naught, times the charge element dq divided by r squared, times the vector r divided by its length. Here the vector r points from the charge element to the point P. In order to determine the electric field E in the point P created by the total amount of the charge Q, we integrate this expression with the infinitesimal charge dq over the whole charge Q. This process can be interpreted as the continuous version of the principle of superposition for electric fields. Then the electric field E in the point P is given by 1 over 4 pi times epsilon naught, times the integral of 1 divided by r squared, times the vector r divided by its length with respect to the charge over the whole macroscopic charge Q. For the sake of completeness, we express the position vector r and the integral as the difference between the vectors rp and r prime, pointing from the reference point O to the point P in the infinitesimal charge dq respectively. The electric field E in the point rp is given by this integral, where the independent variable q, in fact is a function of the position vector r prime. Therefore the independent variable of the integrand can be changed from the charge q to another variable related to the geometry of the problem. Let us see how to proceed with it in the 1, 2 and 3-dimensional cases. We have seen that the infinitesimal charge element dq along a charged wire can be written as the linear charge density lambda times the infinitesimal length dl measured along the curve C. As a result, the electric field E created by a charged wire is equal to 1 over 4 pi times epsilon naught, times the line integral of the charge density lambda divided by r squared, times the vector r divided by r with respect to the length L along the curve C. Here the line element dl can be expressed in the terms of the vector r pointing from the charge elements along the curve to that point, and we can perform the integration with respect to the coordinates of the vector r. For the electric field created by charged surfaces, the infinitesimal charge element dq is given by the surface charge density sigma times the infinitesimal surface element ds. Then the electric field E created by a charged surface S is equal to 1 over 4 pi epsilon naught, times the surface integral of sigma divided by r squared, times the vector r divided by its length, over the surface S. Here the surface element ds can be expressed in the terms of the position vector r, and the independent variable of the integrand can be changed to the coordinates of the vector r. For a spatial distribution of charge, the infinitesimal charge dq is given by the spatial charge distribution ρ times the infinitesimal volume element dv. Then the electric field E created by the charge distributed in the volume V is equal to 1 over 4 pi epsilon naught, times the volume integral of ρ divided by r squared, times the vector r divided by its length, over the volume V. Here the volume element dv can be expressed in the terms of the position vector r, and the independent variable of the integrand can be changed to the coordinates of the vector r. In the first example for the application of charge density, we determine the electric field created by an infinitely long thin straight uniformly charged wire. We approximate the wire with an infinite line, along which the charge is uniformly distributed. The figure shows a section of the positively charged line and the point P where we want to determine the electric field strength. We choose the closest point of the line to the point P as the origin of a Cartesian coordinate system, where the x-coordinate measures the distance along the line. Here the distance of the point P from the line is given by the y-coordinate. For a uniform charge distribution along the line, the infinitesimal charge or the charge element dq in a small portion of the line at the distance x from the origin is equal to the product of the constant charge density lambda and the line element dx measured along the line. Then the contribution dE of the charge element dq to the magnitude of the electric field E is given by 1 over 4 pi epsilon naught, times the ratio of lambda times dx to r squared. Here r is the distance of the line element dx from the point P, which is equal to the square root of x squared plus y squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. If theta is the angle measured between the y-axis and the direction of the line element dx seen from the point P, then the x component of the vector dE can be written as minus dE times sine theta, and its y component is equal to dE times cosine theta. In order to obtain the components of the electric field strength E, we need to integrate the contributions of the charge elements to the field along the line. The x component of the electric field E is equal to the integral of dEx, which can be written as minus the line integral of sine theta with respect to the magnitude of E along the infinite line. Similarly, the y component of the electric field E is equal to the integral of dEy, which can be written as the line integral of cosine theta with respect to the magnitude of E along the infinite line. Since the geometry of the infinite line is reflection symmetric about the origin, for each charge element on the left-hand side of the origin there is a corresponding charge element on the right-hand side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their y components point in the same direction but their x components point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the x direction. That is, the x component of the electric field strength vanishes and it has only a y component. Since the contributions of the charge elements on the left and right-hand sides of the origin are the same, it is enough to take 2 times the integral of the contributions in the y direction over the half of the x-axis. Now we see that the magnitude of the electric field E is equal to its y component, and the substitution of the result obtained for Ey into this formula gives 2 times the line integral of cosine theta with respect to the magnitude of E from the origin of the line to infinity. We have already determined the differential of the magnitude of E, which we can insert into this equation. Then the magnitude of the electric field can be written as lambda over 2 pi epsilon naught, times the integral of cosine theta over x squared plus y squared with respect to x from 0 to infinity. Here cosine theta can be expressed in the terms of the Cartesian coordinates. We see in the figure that the distance x of the line element dx from the origin is equal to the distance y times tangent theta. If we take the differential of this equation, we see that dx is equal to the ratio of y to the square of cosine theta, times d theta. Then dx over x squared plus y squared is equal to the ratio of y times d theta to the square of cosine theta times x squared plus y squared. Since x is equal to y times tangent theta, we have the ratio of y times d theta to y squared times the square of cosine theta, times the square of tangent theta plus 1. After simplifying this expression, we obtain d theta divided by y times the square of sine theta plus the square of cosine theta. Since the square of sine theta plus the square of cosine theta is equal to 1, we obtain that dx over x squared plus y squared is equal to d theta divided by y. If we substitute this result into the integral, the magnitude of the electric field can be written as lambda over 2 pi times epsilon naught times y, times the integral of cosine theta with respect to theta from 0 to pi divided by 2. By performing the integration, we obtain lambda over 2 pi times epsilon naught times y, times the primitive function sine theta evaluated at the lower limit 0 and the upper limit pi over 2. The evaluation gives lambda over 2 pi times epsilon naught times y. Therefore, the magnitude E of the electric field created by a uniformly charged infinite line at any point with the distance y from the line is given by the charge density lambda divided by 2 pi times epsilon naught times the distance y. The electric field points radially away from the positively charged line. This formula shows that the magnitude of the field is inversely proportional to the distance from the line, that is, the electric field of a point charge falls off faster at large distances than the one created by the uniformly charged infinite line or wire. The next example is rather similar to the previous one, where we determine the electric field created by a uniformly charged thin ring on its axis. We suppose that the thickness of the ring is much smaller than its radius and approximate the ring with a circle, along which the charge is uniformly distributed. The figure shows a positively charged circle with the radius R and the point P on its axis where we want to determine the electric field strength. We choose the center C of the circle as the origin of a Cartesian coordinate system, such that the z-axis is perpendicular to the plane of the circle. Here the distance of the point P from the plane of the circle is given by the z-coordinate. For a uniform charge distribution along the circle, the infinitesimal charge dq in a small line element dl of the circle at its intersection with the y-axis is equal to the product of the constant charge density lambda and the line element dl. Then the contribution dE of the charge element dq on the circle to the magnitude of the electric field E is given by 1 over 4 pi times epsilon naught, times the ratio of lambda times dl to small r squared. Here small r is the distance of the line element dl from the point P, which is equal to the square root of capital R squared plus c squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. If theta is the angle measured between the z-axis and the direction of the line element dl seen from the point P, then the y component of the vector dE can be written as minus dE times sine theta, and its z component is equal to dE times cosine theta. In order to obtain the components of the electric field strength E, we need to integrate the contributions of the charge elements to the field along the circle. The y component of the electric field E is equal to the integral of dEy, which can be written as minus the integral of sine theta with respect to the magnitude of E along the circle. Similarly, the z component of the electric field E is equal to the integral of dEz, which can be written as the integral of cosine theta with respect to the magnitude of E along the circle. Since the geometry of the circle is rotational symmetric about its axis, for each charge element on one side of the axis there is a corresponding charge element on the other side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their z components point in the same direction, but their components parallel with the plane of the circle point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the y direction. That is, the y component of the electric field strength vanishes and it has only a z component. Now we see that the magnitude of the electric field E is equal to its z component, and the substitution of the result obtained for Ez into this formula gives the integral of cosine theta with respect to the magnitude of E along the circle. We have already determined the differential of the magnitude of E, which we can insert into this equation. Then the magnitude E of the electric field can be written as 1 over 4 pi times epsilon naught, times the line integral of cosine theta times lambda over capital R squared plus c squared with respect to the length L along the circle. Here cosine theta can be expressed in the terms of the Cartesian coordinates, which is given by the ratio of the distance z to the distance small r. That is, cosine theta is equal to z over the square root of capital R squared plus c squared. If we substitute this result into the integral, the magnitude of the electric field can be written as 1 over 4 pi times epsilon naught, times z over capital R squared plus c squared to 3 over 2, times the integral of lambda with respect to the length L along the circle. We immediately see that the integral is just the integration of the charge along the circle, which gives the total charge Q distributed along the ring. Therefore, we obtain the magnitude E of the electric field created by a uniformly charged ring with a radius R and a total charge Q and a point on its axis at the distance z from the center of the ring, which is given by 1 divided by 4 pi times epsilon naught, times Q times z divided by capital R squared plus c squared to 3 over 2. The electric field of the positively charged ring along the axis is parallel with the axis itself and points outward from the plane of the ring. This formula also shows that the magnitude of the field is inversely proportional to the square of the distance from the ring, if the distance E is much greater than the radius R of the ring. Roughly speaking, the electric field created by a charged ring along its axis looks like the one of a point charge with the same total charge at distances far from the ring. After studying electric fields due to charge uniformly distributed along a line or a curve, we present the electric field generated by surface charges. In the first example, we determine the electric field around a uniformly charged plate or plane sheet extending to infinity. We start with a plate with a finite extension L, and we compute the electric field in the point P on the z-axis of the Cartesian coordinate system attached to the middle of the plate such that the x and y axes are parallel with the edges of the plate. We assume that the distance z of the point P from the plate is much smaller than the length L of the sides of the plate. For a uniform charge distribution over the plate, the charge element dq over any area element ds is equal to the constant surface charge density sigma times the area ds. If we partition the plate into infinitesimally thin strips with the length L and the infinitesimal width dy, then the area ds element can be written as L times dy, and the uniformly distributed charge over each strip is given by sigma times L times dy. We consider the strips with the infinitesimal width as lines with the linear charge distribution lambda, given by the ratio of the charge element dq to the length L of the strips. Since the charge distributed over each strip is equal to the surface charge density sigma times the length L times the width dy, lambda can be written as sigma times dy. Now we determine the electric field created by the infinitesimal charge which is uniformly distributed along a given strip at the distance y from the x-axis. Since the strip is very long compared to the distance r of the point P from the strip, we can apply the result obtained for a uniformly charged infinite line. Then the contribution dE of the charge element dq distributed along a line to the magnitude of the electric field is given by 1 over 2 pi times epsilon naught, times the ratio of the linear charge density lambda to the distance r. Here we already expressed the distance r as the square root of z squared plus y squared. By substituting the product of the surface charge density and the infinitesimal width dy into lambda, we obtain 1 over 2 pi times epsilon naught, times sigma times dy divided by the square root of z squared plus y squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. We obtain the components of the net electric field E in the point P by performing the integration of the contributions of the strips over the whole plane. If theta is the angle measured between the z-axis and the direction of the middle of the strip seen from the point P, then the y component of the magnitude of E is the integral of dEy, which is equal to minus the integral of sine theta with respect to the magnitude of E. Similarly, we obtain the z component of the magnitude of E by performing the integration of dEz, which can be written as the integral of cosine theta with respect to the magnitude E. Since the geometry of the sheet is symmetric about the x-axis, for each strip with their charge element dq on one side of the axis there is a corresponding strip with the same charge element on the other side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their z components point in the same direction but their y components point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the y direction. That is, the y component of the electric field strength vanishes and it has only a z component. Then the magnitude E of the electric field is equal to its z component, which is given by sigma times z over 2 pi times epsilon naught, times the integral of cosine theta divided by the square root of z squared plus y squared with respect to y from minus L over 2 to plus L over 2. Here cosine theta can be expressed in the terms of the Cartesian coordinates, which is given by the ratio of the distance z to the distance r. That is, cosine theta is equal to z over the square root of z squared plus y squared. As a result, we have sigma times z over 2 pi times epsilon naught, times the integral of 1 over z squared plus y squared with respect to y from minus L over 2 to plus L over 2. By performing the integration, we obtain sigma times z over 2 pi times epsilon naught, times the primitive function 1 over z times tangent y divided by z, which we evaluate at the lower limit minus L over 2 and the upper limit L over 2. This formula already gives the electric field strength E on the z-axis erected in the middle of the charged plate with a finite size. However, we are interested in the electric field of a uniformly charged infinite plane and we take the limit of this expression. That is, we determine sigma over 2 pi times epsilon naught times the limit of 1 over the tangent of y divided by z, which we evaluate at minus L over 2 and L over 2 as L tends to infinity. The limit of this expression is equal to sigma over 2 pi times epsilon naught times the difference of pi over 2 obtained at the upper limit of the integration, and minus pi over 2 obtained at the lower limit of the integration, that is pi over 2 plus pi over 2. By simplifying the expression we obtain sigma over 2 times epsilon naught. Then we see that the magnitude E of the electric field is constant over and above the sheet, and it is equal to the surface charge density sigma of the infinite sheet divided by 2 times epsilon naught. The direction of the electric field created by the positively charged sheet perpendicular to the plane of the sheet and points outward on both sides of the sheet. Then we can conclude that the electric field is homogeneous or uniform around a uniformly charged infinite sheet. In the second example illustrating electric charge distributed over a surface, we determine the electric field around a uniformly charged disk, which can be applied to derive the result obtained for the uniformly charged infinite plane sheet by extending the radius of the disk to infinity. For a uniformly charged disk with the radius R, we will compute the electric field in the point P on the z-axis of the Cartesian coordinate system attached to the center of the disk. Then the distance of the point P from the disk is given by the coordinate z. Since the distribution of the positive charge is uniform over the disk, the charge element dq over any area element ds is equal to the constant surface charge density sigma times the area ds. Let us partition the disk into thin rings with the radius r and the infinitesimal width dr. For the sake of brevity, we only use the letter r for the radius of the disk denoted by small r and its differential, as opposed to the radius R of the disk, where we always indicate that it is a capital letter. Then the area element ds of each ring is the difference of the areas of the disks with the radii r plus dr and r. That is, ds is equal to pi times the square of r plus dr, minus pi times r squared, which is equal to pi times r squared plus 2 pi times r times dr, plus pi times dr squared minus pi times r squared. Here we can neglect the term pi times dr squared, which is second order in the infinitesimal width dr of the ring. Then we can approximate ds with the expression 2 pi times r times dr. Thus we have partitioned the disk into rings with the radius r and the width dr, which have the infinitesimal area 2 pi times r times dr. As a result, the charge element dq over each ring is given by 2 pi times the surface charge density sigma, times the radius r of the ring, times the width dr of the ring. Now we determine the electric field along the axis of the disk, which is created by the infinitesimal charge uniformly distributed along a given ring. For such a geometry we can apply the result obtained for a uniformly charged ring. Here we show the contribution dE of the charge element dq distributed along a ring to the magnitude of the electric field in the point P located at the distance of the square root of r squared plus d squared from the ring. The contribution dE is parallel with the z-axis and points outward for the positively charged disk due to the axial symmetry of the charge distribution. We also have seen that the magnitude of dE is given by 1 over 4 pi times epsilon naught, times the ratio of the distance z times the charge element dq to r squared plus c squared to 3 over 2. By expressing the charge element in terms of the surface charge density, we obtain 1 over 4 pi times epsilon naught, times 2 pi times sigma times r times dr divided by r squared plus c squared to 3 over 2. The magnitude E of the electric field in the point P on the axis can be determined by integrating the contribution dE of each ring over the whole disk. This gives sigma times z over r 2 times epsilon naught, times the integral of r divided by r squared plus c squared to 3 over 2 with respect to r from 0 to capital R. We can change the variable of the integration by introducing the variable u for the expression r squared plus c squared, where the differential du is given by 2 times r times dr. The lower limit of the integration becomes z squared, and its upper limit will be the square of capital R plus c squared. As a result, we have sigma times z over 4 times epsilon naught, times the integral of u to minus 3 over 2 with respect to u from z squared to the square of capital R plus c squared. By performing the integration, we obtain sigma times z over 4 times epsilon naught, times the primitive function u to minus half divided by minus half, which we evaluate at the upper limit of the square of capital R plus c squared and at the lower limit z squared. Then the result is equal to minus sigma times z over 2 times epsilon naught, times 1 over the square root of the square of capital R plus c squared, minus 1 over the square root of z squared. We can factor out 1 over z from the terms in the parentheses, and we get sigma over 2 times epsilon naught, times plus or minus 1, minus 1 over the square root of 1 plus the square of capital R divided by z squared. Here we use the plus sign in the first term in the parentheses if z is positive, that is if the point P is located above the disk, and the negative sign if the z is negative, that is if the point P is located under the disk. Since the problem is reflection symmetric about the plane of the disk, we only use the expression describing the field above the disk. Then we have determined the magnitude E of the electric field due to the uniformly distributed charge over a disk with the radius capital R and the point P on its axis at the distance c, and it is given by sigma times E over 2 times epsilon naught, times 1 minus 1 over the square root of 1 plus the square of capital R divided by z squared. The electric field strength E in the point P is parallel with the z-axis and points outward from the disk. If the radius capital R of the disk tends to infinity, that is the distance z is negligible to the radius capital R, then the second term in the parentheses becomes negligible, and the whole expression approximates sigma divided by 2 epsilon naught, as we expected. That is, the electric field around the axis of a large charged disk is uniform, and perpendicular to the plane of the disk. We can apply the result obtained for a uniformly charged infinite plane sheet to determine the electric field created by two uniformly charged infinite parallel planes. We assume that one of planes has the surface charge density sigma and the other one has minus sigma, that is the planes have the same amount but opposite charges plus q and minus q. First, we choose the point PL on the left-hand side, the point PB between the two planes and the point PR on the right-hand side where we examine the properties of the uniform electric fields due to the charged planes. Since the electric field E sub plus created by the positively charged plane points outward, it points to the left in the point PL, and points to the right in the points PB and PR. In contrast, the uniform electric field E sub minus created by the negatively charged plane points inward, therefore it points to the right in the points PL and PB, and points to the left in the point PR. We have already seen that the magnitude of the electric field due to a uniformly charged infinite sheet is equal to its surface charge density divided by 2 times epsilon naught. That is, the magnitudes of both the electric fields E sub plus and E sub minus are equal to sigma over 2 times epsilon naught. The only difference between these fields is that the field E sub plus points outward and the field E sub minus points inward. Now we can apply the principle of superposition for electric fields to determine the net electric field E created by both the charged planes. We start with the net electric field in the point PB located in the space between the planes. As the figure shows, both the electric fields E sub plus and E sub minus point in the same direction in that point. Therefore we can write that the electric field E sub plus is equal to the electric field E sub minus, and this relation holds everywhere between the planes. As a result, the superposition of the two vector fields is just the algebraic sum of their magnitudes, that is the magnitude E of the net field is equal to the sum of the magnitudes of E sub plus and E sub minus. If we substitute the equations obtained for E sub plus and E sub minus, this sum can be written as sigma over 2 times epsilon naught plus sigma over 2 times epsilon naught, which gives sigma over epsilon naught. By comparing the result with the fields E sub plus and E sub minus, we can see that the magnitude of the net electric field strength is 2 times greater than the fields created by the charged planes but it points in the same direction. That is the field E points from the positively charged plane towards the negatively charged one. If we consider the points PL and PR on the left and right-hand sides of the pair of the planes, we see that the electric fields E sub plus and E sub minus point in opposite directions. This fact can be expressed by the vector equation stating that the electric field E sub plus is equal to minus the electric field E sub minus outside the space between the planes. As a result, the magnitude E of the net electric field on those spatial domains is given by the difference of the magnitudes E sub plus and E sub minus. Then we have sigma over 2 times epsilon naught minus sigma over 2 times epsilon naught, which gives 0. That is, in the left and right-hand side regions of the planes the electric fields E sub plus and E sub minus cancel out and the net electric field E vanishes. Then we can conclude that the electric field E is uniform in the space between two parallel uniformly charged infinite planes with the same but opposite charges. Its magnitude is equal to the surface charge density sigma of the planes divided by epsilon naught, and the field points from the positively charged plane towards the negatively charged one. The electric field E is 0 everywhere else. This result also holds for charged finite plates with the same size, provided the distance d between them is much smaller than their linear extension L. Here we can see a capacitor consisting of two metal discs with a given radius and an apparatus used to modify the distance between the two plates, so that one can study the homogeneity of the field between the plates for different distances. When we studied the interaction between electric charge and electric field, our goal was to determine the electric field created by point charges or some spatial distribution of charge, and compute the electric field strength representing the field in each point of the space. Now we look at this interaction from the opposite point of view. Our purpose is to examine the force and the torque acting on the point charges or dipoles in a given electric field. For example, if a point-like particle with the charge q and the mass m is placed in an electric field E, then the field exerts a force F on the particle, which is by definition equal to the charge q times the electric field strength E in the position of the particle. The force F will accelerate the particle, and its acceleration A is given by the force F divided by the mass m. If we substitute the expression obtained for the electrostatic force into this equation, we can see that the acceleration is equal to q times E divided by m. Here the acceleration of the particle is directly proportional to the field strength E in the instantaneous position of the particle and its charge, and inversely proportional to its mass. In the study of the motion of charged particles in electric fields, we will neglect the effect of gravity on the moving particle and the back reaction of the charge carrier moving in the electric field, that is the effect of the point charge on the source charges of the field. We neglect the radiation effects as well, which we will study later. Now we will examine the motion of an electron in a homogeneous or uniform electric field. The charge of an electron is equal to minus the elementary charge E, and we denote the mass of the electron by me. In the experiment setup we use two parallel plates with the same but opposite charges where the distance between the plates is much smaller than their size. For such an arrangement the electric field E is uniform in the space between the plates, and points from the positively charged plate towards the negatively charged one. Let us place an electron in a point close to the negatively charged plate. Since the free electron is at rest, its initial velocity v0 is equal to 0. We choose the vertical y-axis such that the electron is at its origin and the axis is oriented upward. The electron experiencing the electrostatic force of the field starts to move in the direction opposite to the electric field, that is towards the positively charged plate. Since the electric field E is uniform, the force acting on the electron is always the same along its trajectory and the acceleration of the electron is constant. Then we can compare the motion of the electron to the free fall of a body under the influence of gravity. The second-order time derivative of the y-coordinate, that is the acceleration A of the electron, is equal to the elementary charge small e times the magnitude capital E of the electric field over the mass me of the electron. Here the minus sign indicates that the acceleration points downward. The integration of this equation gives the first-order time derivative of the y-coordinate, that is the instantaneous velocity v of the electron, and it is equal to the product of the acceleration A and the time t, that is minus small e times capital E over me, times t. If we integrate this equation, we can write the distance y covered by the moving electron as a times t squared over 2, which is equal to minus small e times capital E over 2 times me, times t squared. Since the charge and the mass of an electron are given, the covered distance y, the velocity v, and the acceleration a of the electron in the uniform electric field depend solely on the constant magnitude E of the field strength. If the electron enters in the uniform electric field E with an initial velocity v0 perpendicular to the field lines, then its motion is similar to the one of a projectile moving in the gravitational field. Here we orient the x-axis of the Cartesian coordinate system along the direction of the initial velocity v0. Then the position of the electron in the x direction is given by the initial velocity v0 times the time t, its time derivative is equal to the constant initial velocity v0, and its second-order time derivative vanishes, indicating that the electron has a uniform rectilinear motion in the direction of the x-axis. At the same time, the y-coordinate of the moving charge carrier is still equal to minus small e times capital E over 2 times me, times t squared, with the time derivative minus small e times capital E over me, times t, and the second-order time derivative minus small e times capital E over me, indicating that the electron has a uniformly accelerating motion in the direction of the y-axis. If we eliminate the time t from these two equations, we can express the y-coordinate of the moving electron as minus small e times capital E over 2 times me times v0 squared, times x squared, which is the equation of a parabola. Therefore, the components of the equations of motion in the directions parallel with and perpendicular to the electric field line show that an electron has a horizontal projectile motion, and propagates along a parabola with a horizontal axis in a uniform electric field, provided it has a non-zero initial velocity. If its initial velocity is not perpendicular to the field lines, then we can talk about a general projectile motion, where the parabolic trajectory of the electron is tilted. One of the most famous examples for the motion of charge carriers in an electric field is the oil drop experiment conducted by Robert Millikan, in which he measured the elementary electric charge. Millikan studied the motion of electrically charged oil drops under the simultaneous influence of gravity and a uniform electric field. The apparatus used in his experiment is a closed chamber, which we can see in the photo. Inside the chamber, a parallel pair of horizontal metal plates is installed to produce a uniform electric field in the space between the plates, when they are charged with the same but opposed charges. A fine mist of oil droplets is sprayed into the space of the chamber above the plates by an oil atomizer. Due to gravity, the droplets fall, and some of them enter the space between the plates through a small hole in the top plate. When the air between the plates is ionized by a radiation from an X-ray source, the free electrons in the air attach to the falling droplets, making them negatively charged. The experiment starts with the measurement of the velocity v1 of the droplets without electric field. Due to the net effect of gravity and the buoyant force, the falling droplets will accelerate until reaching their terminal velocity, since the drag force representing the air resistance compensates the net effect accelerating the droplets. The net force F of the gravitational and the buoyant forces can be written as the volume V of the droplet times the difference of the density ρ of oil and the density ρ of air, times the gravitational acceleration g. Since the shape of a droplet can be approximated with a sphere, its volume is given by 4 pi over 3 times r cube, where r is the radius of the sphere. This formula can be substituted into the net force, and we obtain 4 pi over 3 times r cube, times ρ oil minus ρ air, times g. Stokes' law determines the drag force acting on the falling droplet, which is equal to 6 pi times the dynamic viscosity eta of the air, times the radius r of the droplet, times the velocity v1 of the droplet. For a droplet moving with the constant speed v1, the balance equation of the forces states that the magnitude of the net force of the gravitational and the buoyant forces is equal to the magnitude of the drag force. In the second step of the experiment, the velocity v2 of the droplets is measured in the uniform electric field between the charged plates. By adjusting the electric field strength, the speed of the charged droplets moving in the field can be increased or decreased. Then the magnitude of the field can be modified until the given droplet is suspended in mechanical equilibrium, indicating that the electric force, the net effect of the gravity and the buoyant force, and the drag force are in balance. Here the electric force exerted on the droplet is given by the charge Q of the droplet times the electric field strength E. The magnitude of the electric field can even be raised so that the droplet starts to move upward, and then reduced to its balance value. As a result, the forces acting on the droplet are in balance again, and the droplet has a uniform linear motion with a constant speed v2. Then the balance equation for the magnitudes of the forces states that the electric force Q times E minus is equal to the net force of the gravitational and the buoyant forces, plus the drag force acting on the droplet at the speed of v2. If we substitute the net force from the first balance equation into the second one, we can write that Q times E is equal to the sum of the drag forces acting on the droplet when it has the speed v1 and v2. By applying Stokes' law, we can express the charge Q as 6 pi times eta times r over E, times the sum of the v1 and v2. As a result, for a given magnitude E of the electric field, the charge of the droplet is determined by its radius r and the velocities v1 and v2 measured in the experiment. The radius r can simply be determined from the first balance equation, since r squared is given by 9 times eta times v1 over 2 times g times the difference of ρ oil and ρ air. If the densities of oil and air, the viscosity of air and the gravitational acceleration are known, the charge Q could be determined by measuring the velocities v1 and v2 of a droplet for a given electric field strength E. Millikan performed a series of measurements in his experiment, and he found that the values of the charge Q attained by the individual droplets are always an integer number multiples of the elementary charge E, which is equal to 1.6021 times 10 to minus 19 Coulomb. The relative error of the experiment was only 0.6% due to the error in the viscosity of air, which was corrected later. We note that Helmholtz already recognized that Faraday's laws of electrolysis have an important consequence. If matter consists of atoms, then charge has necessarily a quantum nature. There must exist an elementary charge, and any macroscopic charge is an integer multiples of this elementary charge. Helmholtz also determined its value as the ratio of Faraday constant to Avogadro's number. However, this ratio gives the average value of the charges of many ions, whereas the oil drop experiment determined the charge of individual ions. After examining the force exerted on a point charge or a charge carrier by an electrostatic field, we will turn to the study of dipoles and electric fields. Let us place an electric dipole in a uniform electric field, where phi is the angle between its dipole moment p and the electric field strength E. Then the forces F and minus F acting on the individual charges plus Q and minus Q of the electric dipole have the same magnitude and opposite direction separated by a perpendicular distance d times sine phi. This pair of forces makes a couple. As usual, E is also represented by a vector pointing from the charge minus Q to the charge plus Q. The electrostatic forces F and minus F are given by Q times E, and minus Q times E. The couple has a turning effect on the dipole about an axis of the dipole perpendicular to the plane of the forces. This turning effect is the moment of the couple or the torque tau with regard to its rotation axis, and it is given by the cross product of the distance vector d and the electrostatic force F. Then the torque tau can be written as the vector product of d and q times E, or the vector product of q times d and E. But q times d is just the dipole moment P, and we can conclude that the torque tau acting on a dipole in a uniform electric field is given by the cross product of the dipole moment P and the field strength E of the electric field. We can write the magnitude of tau as the product of the magnitudes of P and E, times the sine of the angle phi measured between them, and the torque is perpendicular to the plane spanned by the dipole moment and the electric field strength. As already mentioned, the torque represents a turning effect, and it attempts to twist the dipole in the direction of the electric field. We also see that the net force of the couple acting on the dipole is zero, that is, the center of the dipole has no acceleration. We can study this effect with an insulating rod with a small metal sphere attached to both ends, which can spin around its midpoint. If we charge the metal spheres with the same but opposite charges and place the apparatus in a uniform electric field E, then it behaves as a dipole in the electrostatic field. The torque attempts to align the dipole to the straight field lines, but at the same time the body starts to oscillate about its rotation axis due to the inertia of the system of the rod and the spheres. Newton's second law of rotation can be applied here, which states that the torque acting on a rigid body about a fixed axis is equal to its moment of inertia, times the angular acceleration. Then the moment of inertia I times the second order derivative of phi with respect to the time is equal to minus the product of the magnitudes of the dipole moment P and the electric field E, times sine phi. The minus sign indicates that the torque tries to restore the direction of the dipole aligned to the electric field. Since we talk about an oscillation with a small amplitude, that is, the angle phi is small, we can approximate the sine of phi with phi in the first order. Then we can write that I times phi double dot is equal to minus P times E times phi, or phi double dot is equal to minus omega squared times phi, where omega square is defined as the ratio of P times E to I. The solution of this differential equation is the rotation angle phi as a function of the time t, which is equal to an amplitude c of the oscillation, times the sine of omega times t. The amplitude c is a constant of integration which can be determined by the initial value condition, that is the initial direction of the dipole with respect to the electric field. The solution shows that the system of the rod and the charged spheres performs a small oscillation in the uniform electric field with the angular frequency omega. We can also give the period t of the harmonic motion of the dipole in the electric field defined as 2 pi over omega, which is equal to 2 pi times the square root of the ratio of I to P times E. The greater the electric field and the dipole moment are and the smaller the moment of inertia is, the greater the frequency of the oscillation or the smaller its period is. Electric dipoles have a potential energy in an electric field, and the definition of the potential energy of a dipole placed in a uniform electric field is very simple. Let us consider a dipole with the dipole moment P in a uniform electric field E, where the angle between the dipole moment and the direction of the field is equal to phi null. The potential energy of the dipole is determined by the work that any external force needs to do on the dipole to change its direction in the electric field. We can compute the work W by integrating the magnitude of the torque tau acting on the dipole with respect to the angle from phi null to phi. Since the torque tau is given by the cross product of the dipole moment and the electric field strength, we have P times E times the integral of sine phi with respect to phi from phi 0 to phi. By performing the integration, we obtain P times E times the difference of cosine phi null and cosine phi. We are interested only in the change in the potential energy and we fix the initial orientation angle. If we set phi null to 90 degrees or pi over 2 given in radian, then the cosine of phi null vanishes. As a result, we can define the potential energy as the work done on the dipole by the electric field turning the dipole from the inclination angle of pi over 2 to the angle phi. That is the work W, called the potential energy U, is equal to minus P times E times cosine phi. Since phi is the angle between the vectors P and E, we conclude that the potential energy U of an dipole with the dipole moment P in a uniform electric field E is given by minus the scalar product of the dipole moment P and the electric field strength E. If the direction of the dipole is perpendicular to the field lines of the uniform electric field, that is the direction angle of the dipole moment P is equal to pi over 2, then the scalar product vanishes and the potential energy of the dipole is equal to 0. If the dipole moment P and the electric field strength E point in the opposite directions, that is phi is equal to pi, the potential energy U of the dipole has the maximum value, which is P times E. If the dipole pointing in the direction of the electric field strength has the minimum potential energy, given by minus P times E. In that point the dipole is in a stable equilibrium, and any small change in the direction of the dipole results in a torque turning back it to its direction parallel with the field. Therefore the angle 0 represents the minimum of a potential well of the dipole in the electric field, indicating that the dipole is aligned with the electric field lines. If we rotate the dipole against the torque exerted on the dipole by the field, we increase its potential energy till its dipole moment points in the opposite direction to the field. In that direction the dipole reaches its maximum potential energy where it has an unstable equilibrium. For any small change in the direction of the dipole, the torque twists the dipole from its anti-parallel position to the parallel one, pushing it towards the bottom of the potential well. Now we consider a more general case where we study the effect of an inhomogeneous electric field on a dipole. In an inhomogeneous electric field E, the magnitude and the direction of the electric field strength depends on the position. If an electric dipole with a pair of point charges plus Q and minus Q is in the electric field E, then the magnitude of the electrostatic force F sub plus acting on the charge plus Q and the force F sub minus acting on the charge minus Q are not necessarily equal. If the position vector points from the reference point O to the charge minus Q of the dipole, then the force pair acting on the dipole is the following. The force F sub plus is equal to the charge Q times the electric field strength E in the point given by the vector sum of the position vector R and the displacement vector D, whereas the force F sub minus is equal to the charge minus Q times the electric field strength E in the point determined by the position vector R. As a result, the net force F acting on the dipole is given by the vector sum of F sub plus and F sub minus, that is Q times E evaluated at R plus D, minus E evaluated at R. The first term in the square brackets can be approximated with its Taylor expansion around the point R in the first order, which gives Q times E evaluated at R, plus the directional derivative of E along with the displacement vector D evaluated at R, minus E evaluated at R. If we assume that the distance d between the charges plus Q and minus Q is small compared to distances over which the field varies, the limit of the ratio or the change of rate of the electric field strength will approximate the right-hand side as the distance d approaches 0. Then the net force F is equal to Q times the directional derivative of the vector field E along the displacement vector D. Since the dipole moment P is equal to Q times the vector D, the net force F acting on the dipole with the dipole moment P in an inhomogeneous electric field is given by the directional derivative of the electric field strength E along the dipole moment P. In the Cartesian coordinate system, the ith component of the force F is equal to px times the partial derivative of the ith component with E with respect to x, plus py times the partial derivative of the ith component with E with respect to y, plus pz times the partial derivative of the ith component with E with respect to z. Here the index I represents the Cartesian coordinate components of the vectors F and E. If we place an electrically neutral conductor in an electric field, then it becomes a dipole due to the separation of charges. Therefore, the effects of the electric field on the conductor can be explained by applying these simple cases presented here. In a uniform electric field, a torque tries to turn a metal rod until its longitudinal axis is parallel with the field lines. As soon as the rod is aligned with the uniform electric field, the torque acting on it vanishes. In another example, we charge a glass rod by rubbing it with leather, and an electrically neutral sphere becomes a dipole due to the separation of charge in the electric field of the charged glass rod. The inhomogeneous electric field of the rod will attract the sphere since the field exerts a force on the dipole in the direction of the increasing field. By introducing the concept of electric flux, we can elucidate the topological properties of electric field. The electric flux or the flux of an electric field is defined as the number of the electric field lines that intersects a given area. With other words, the flux is the rate of flow of the electric field through a surface per its area. If the electric field E is uniform, the electric flux phi E passing through a planar surface S perpendicular to the field lines is given by the magnitude E of the electric field, times the surface area S. If theta is the angle between the direction of the field lines and the normal n of the planar area S, then the electric flux phi E is equal to E times S times cosine theta, that is E times the area S perp projected into the direction of the field lines, or equivalently, the projection En of the electric field strength on the surface normal n, times the surface area S. By introducing the area vector for the surface S as the surface area S times the surface normal n, we can write the flux phi E as the scalar product of the electric field strength E and the area vector S. Let us consider a more general case where the electric field E is not uniform and the surface S has an arbitrary shape. We partition the surface S into the surface area elements delta Si, such that they are small enough to be approximated with planar area elements over which the electric field EI can be considered constant. Then the electric flux phi E through the surface S can be approximated with the scalar product of EI and delta Si from I equals to 1 to n. Here n is the number of the area elements covering the surface S. If we refine the partitioning of the surface S such that the area delta Si approaches 0 for each index I while the number of the area elements tends to infinity, we obtain a surface integral from the sum. That is, the electric flux phi E through a surface S is given by the integral of the electric field strength E over the surface S. In the case of closed surfaces we can apply the same method, and the electric flux phi E intersecting the closed surface S is also given by the surface integral of the electric field strength E over the closed surface. By convention, the area element vector ds on a closed surface is directed perpendicularly outwards, that is, its direction in a given point on the surface is given by the outward surface normal in that point. For the electric field lines piercing the closed surface S, the surface can be split into the part S1, where the field lines are directed out of the closed surface, and the part S2, where the field lines are directed into the closed surface. In the first case the angle between the surface normal and the electric field strength E over the surface S is less than pi over 2. Therefore, the scalar product of these vectors is greater than 0, and the electric flux is positive over the surface S1. On the contrary, the angle between the surface normal and the electric field strength E is greater than pi over 2 over the surface S2, and the electric flux through the surface S2 is negative. As a result, if all the electric field lines entering into the volume enclosed by the surface exit the volume, then the total electric flux through the surface vanishes. With other words, if no electric field lines originate or terminate within the volume enclosed, the net electric flux through the closed surface S is 0. Now we can determine the flux through an arbitrary closed surface for the electric field due to a point charge. We calculate the electric flux when the point charge is inside and outside the volume enclosed by the surface. We start with the simplest case, where a positive point charge Q is placed at the center of a spherical surface S with the radius r. Then both the electric field strength E due to the point charge and the surface normal A are perpendicular to the sphere in its each point. As a result, the electric flux phi E through the sphere is equal to the magnitude E of the electric field measured at the surface, times the total area S of the sphere with the radius r. The first factor of the product is given by Coulomb's law, which states that the magnitude E of the electric field at the distance r from the point charge Q is equal to 1 over 4 pi times epsilon naught, times Q divided by r squared. The second factor, that is the surface area of the sphere, is given by 4 pi times r squared. As a result, we can write the flux as the charge Q over 4 pi times epsilon naught times r squared, times 4 pi times r squared. Then we obtain Q divided by epsilon naught. Since the flux through the closed surface S is the surface integral of the electric field strength over the surface, we can conclude that the surface integral of the electric field strength E of the point charge Q over the sphere S with the point charge in its center gives the charge Q divided by epsilon naught. If the point charge Q is inside a closed surface S of an arbitrary shape, we can calculate the flux element through an infinitesimal area element ds on the surface. The flux element d phi E is given by the dot product of the electric field E at the area element and the area element vector ds. The dot product can be written as the magnitude of the electric field at the area element, times the area ds times cosine theta, where theta is the angle between the direction of the electric field at the area element, and the normal n of the area element. If d omega is the solid angle subtended by the surface element ds, then the projection dsr of the surface element perpendicular to the electric field E also subtends the solid angle d omega at the distance r from the point charge. Here ds times cosine theta is the projected area element dsr. Then we can apply Coulomb's law, and write the flux d phi E as Q over 4 pi times epsilon naught, times dsr over r squared. But the projected area element dsr is equal to the square of the distance r, times the solid angle d omega subtended by the area element. As a result, we obtain Q over 4 pi times epsilon naught, times d omega. We have already seen that the integral of the electric field over the closed surface S is equal to the electric flux phi E through the surface, which is given by the integral of the contribution d phi E over the whole closed surface S. By substituting the result we derived above, we obtain q over 4 pi times epsilon naught times the integral with respect to the solid angle over the whole surface S. If the surface S is such that the lines originating from the point charge q intersect the surface only once, then the integral represents the solid angle subtended by the unit sphere, which is 4 pi. This gives q over epsilon 0, as in the case of the sphere. In the case of a surface where the lines originating from the point charge q intersect the surface more than once, we proceed as follows. For example, if the lines originating from the point charge intersect the surface 3 times, then the surface area elements subtending the solid angle d omega are ds1, ds2 and ds3. Since the electric field of the point charge is spherically symmetric, the magnitude of its flux is the same through all the 3 area elements. The only difference is that the flux is positive over the area elements ds1 and ds3, and negative over the area element ds2, which can be seen the angles between the directions of the area element vectors and the one of the electric field. As a result, the fluxes through the area elements ds2 and ds3 cancel out, and only the flux over the area element ds1 has a contribution to the net flux over the whole surface S. Whenever the number of the intersections is odd, we have the same result. Then the projections of the area elements providing a contribution to the net flux cover a whole sphere with the point charge in the center without overlapping each other, and the integral gives the solid angle subtended by the sphere again, which is 4 pi. Now we can conclude that if a point charge q is in the volume enclosed by an arbitrary surface S, then the integral of the electric field due to the charge over the surface S is equal to charge q divided by epsilon naught, as in the case of the sphere. After having determined the flux through a closed surface due to a point charge enclosed the surface, let us examine the case where the positive point charge q is outside the closed surface S. Since the flux phi E is given by the integral of the electric field E due to the charge q over the surface S, we can follow the procedure which we discussed in the case of the flux through closed surfaces in an inhomogeneous electric field. We split the surface S into the part S1 where the electric field lines are directed out of the closed surface, and the part S2 where the field lines are directed into the closed surface. Then we can also split the integral into 2 parts, that is the sum of the integrals of the electric field E over the surfaces S1 and S2. The first term is the electric flux through the surface S1 and the second one the flux through the surface S2, and these fluxes contribute to the net flux phi E through the closed surface S. We have also seen that the contribution of the field lines entering the volume enclosed by the surface S is the same as the one of the field lines exiting the volume. The only difference is that the first one is negative and the latter one is positive, that is the flux through the surface S1 is equal to minus the flux through the surface S2. As a result, the flux E through the closed surface S for the electric field E due to the point charge q outside the volume enclosed by the surface vanishes. Now we conclude that the electric flux through an arbitrary surface S enclosing a given volume for the electric field E due to a point charge q is determined by the integral of the electric field strength E over the surface, and it is equal q over epsilon naught, if the point charge is within the volume enclosed by the surface, and 0 otherwise, that is the point charge q is outside the closed surface. We note that we applied Coulomb's law for a single point charge to derive this relationship between electric flux and charge. The question is whether we can extend this result to multiple point charges, or even to a continuous distribution of charge. If we examine this question, we will see that such an extension of this result is possible, which is stated in Gauss's law. First we show how to extend the result to an electric field due to a system of point charges. Let us suppose that the point charges q1, q2, ellipsis, qn are within the volume enclosed by an arbitrary surface S. The total charge q in the volume is the algebraic sum of the charges qi in the system from I equals 1 to n. The principle of superposition for electric fields states that the net electric field strength E due to the system of the point charges is the vector sum of the electric field strengths EI due to the individual point charges qi from I equals 1 to n. By virtue of Coulomb's law, the electric field EI in a given point is equal to 1 over 4 pi times epsilon naught, times qi over the square of the distance Ri between the point charge qi at that point, times the distance vector Ri pointing from the point charge to that point, divided by its length. Since the electric flux phi E through the surface S is the integral of the net electric field E over the surface S, it is equal to the integral of the sum of the electric fields EI from I equals 1 to n over the surface S. If we exchange the integral and the summation, we can write that the flux is equal to the sum of the integrals of the individual electric fields EI over the surface S from I equals 1 to n. For the electric fields EI due to the individual point charges qi, we can use the result we have already obtained, and state that the integral of the electric field strength EI over the surface S is equal to the charge QI divided by epsilon naught for I equals 1 to n. If we substitute this equation into the sum, we will obtain Gauss's law, which is related to Gauss's theorem proved by Carl Friedrich Gauss, and states the following. The electric flux through an arbitrary closed surface S is equal to the sum of the charges enclosed by the surface, times 1 over epsilon naught, that is the total charge Q within the volume enclosed by the surface, times 1 over epsilon naught. If a point charge is outside the closed surface, then it has no contribution to the electric flux through the surface. In the next step, we will extend Gauss's law to electric fields due to continuous distributions of charge, where the distribution of a charge enclosed by a surface can be arbitrary. We can consider not only a system of point charges within a volume enclosed by a surface S, but also a charge distributed continuously along a curve calligraphic C with a linear charge density lambda, over a surface calligraphic S with the surface charge density sigma, or in a volume calligraphic V with the spatial charge density ρ, all enclosed by the surface S. In fact, the system of point charges and the charge distributed along a curve or over a surface are special cases of the charge distributed throughout a volume, where the spatial charge distribution is restricted to a set of points, along a curve, or over a surface. Therefore, we use the most general case with the spatial distribution of charge to extend Gauss's law to a continuous distribution of charge. Then Gauss's law for a charge distributed in a volume calligraphic V enclosed by the surface S can be written as follows. The integral of the electric field E due to the charge over the closed surface S is equal to 1 over epsilon naught, times the integral of the charge density ρ over the volume calligraphic V. By applying Gauss's theorem, we can transform the surface integral in the left-hand side of the equation to a volume integral. Then the integral of the divergence of the electric field strength E over the volume calligraphic V enclosed by the surface S is equal to 1 over epsilon naught, times the integral of the charge density ρ over the volume calligraphic V. Since the surface S, that is the volume calligraphic V enclosed by it, is arbitrary, the relation holds for any volume, and the integrands on both sides must be equal. As a result, we obtain Gauss's law in differential form, stating that the divergence of the electric field strength E is equal to the electric charge density ρ divided by epsilon naught. As opposed to the integral form of Gauss's law, the differential form describes a local relationship between the electric field and the spatial distribution of charge. The law states that the electrostatic field is a vector field, that is, describe the electric field strength E in each point of the space, which has sources. The sources of the electric field are charges, or more generally an arbitrary spatial distribution of charge, and the divergence of the electric field measures the intensity of the sources. Before presenting some applications of Gauss's law, we make a few remarks on the relationship between Gauss's law and Coulomb's law. Gauss's law and Coulomb's law are two different forms of the same fundamental law describing the interaction between electric charge and electrostatic field. This statement follows from the fact that Gauss's law is derived from the basic assumption that the interaction between electric charge and electric field is inversely proportional to the square of the distance between the charge and the source charge of the field. It is easy to see that Gauss's law does not hold for any interaction proportional to the distance to the power n, if n is not equal to -2. Let us derive the electric flux phi E through a sphere S with the point charge Q in its center for n equals to -3. Then the surface integral of the electric field strength E due to the charge over the sphere S is given by the magnitude E of the field strength over the sphere times the area S of the sphere. Since the area of the sphere is equal to 4 pi r squared and n is equal to -3, we have Q over 4 pi times epsilon naught times r cubed, times 4 pi times r squared, which gives 1 over epsilon naught, times the charge Q over the distance r. As a consequence, the electric flux through the sphere S with a finite radius r for a point charge Q in its center has a non-zero value. However, by increasing the radius r of the sphere and therefore its area S to infinity, we can diminish the electric flux through S to zero, meanwhile the amount of charge remains the same in the sphere. This result contradicts Gauss's law. We also note that Coulomb's law can always be used to determine the electric field due to a given distribution of charge. However, with few exceptions, it is a complicated procedure. Gauss's law can primarily be applied for highly symmetric distributions of charge, which provides a very simple method to determine the electric field strength. In the integral form of Gauss's law describing the relationship between electric field and charge, the electric field E in the integrand is not necessary due to the charge Q in the right-hand side enclosed by the surface S. Here we can see that the electric field and the flux through the surface S do not vanish. At the same time, the electric field strength due to the charge enclosed by the surface S is zero, and so does the electric flux through the surface, since the volume enclosed by the surface is free from charge. Therefore, the electric field E in Gauss's law can be due to charges both inside and outside the volume enclosed by the surface S. In order to present some applications of Gauss's law, we need to clarify the concept of Gaussian surface, as the key element of the law. We have defined electric flux by introducing an imaginary surface and determining the number of the electric field lines passing through that surface. When we proved Gauss's law, we applied a surface enclosing a source charge over which we evaluated the electric field due to the charge. We call such a surface as Gaussian surface. That is, Gaussian surface is any imaginary surface that encloses a charge or an arbitrary distribution of charge. Although Gauss's law applies to any closed surface, it is often convenient to choose such a surface which helps us to exploit the symmetry of the charge distribution. The electric field due to a symmetric distribution of charge also exhibits that symmetry in some form, and we can find a Gaussian surface on which the magnitude of the electric field is constant and the electric flux is normal or tangent to the surface. Let us consider some simple examples for Gaussian surface. The first one is a sphere S enclosing a point charge Q in its center. If we forget about Coulomb's law, we can still suppose that there is no preferred direction around a point charge. Therefore, the electric field E must be spherical symmetric around it, as the radial field lines demonstrate. Since the magnitude of the electric field is the same in every direction at a given distance from the source charge, it is constant over the sphere S. At the same time, the electric field is perpendicular to the Gaussian surface. Another example for Gaussian surfaces is a cylinder denoted by S around an infinite charged line with a constant linear charge density lambda. Since the electric field E for such a uniform distribution of charge has a cylindrical symmetry around the line, the electric field is normal to the curved surface of the cylinder and the magnitude of the field is constant over it. The electric field is tangent to the two parallel planes of the cylinder, that is, the field lines do not intersect them. The amount of charge Q enclosed by the cylinder is the source of the electric field which we evaluate on the Gaussian surface. In the third example, we also use a cylinder as a Gaussian surface denoted by S, which is cut in half by a uniformly charged infinite plane sheet perpendicular to the axis of the cylinder. Here the surface charge density sigma is constant over the plane. Since the electric field E points outward from the positively charged sheet and it is uniform, the field is perpendicular to the parallel bases of the cylinder and its magnitude is constant over them. The electric field lines are parallel with the curved surface of the cylinder and do not pass through it. The amount of charge Q enclosed by the cylinder is the source of the electric field which we evaluate on the Gaussian surface. These examples demonstrate that we have two cases in the calculation of the electric flux through Gaussian surfaces. Where the electric field is normal to the Gaussian surface and its magnitude is constant, the electric flux through the surface can be evaluated by multiplying the magnitude E of the field and the area S of that portion of the surface. Where the electric field is tangent to the Gaussian surface, the field lines do not cross the surface, therefore the electric flux through that portion of the surface vanishes. With the proper choice of the shape of a Gaussian surface, we can decompose the total closed surface into partial surfaces over which the surface integrals of the electric field either reduce to a simple multiplication or vanish. The net electric flux over the total surface is just the algebraic sum of the fluxes through the partial surfaces. Now we start with the simplest example for the application of Gauss's law, where we determine the electric field due to a point charge. We have already seen that the electric field E due to a positive point charge Q has a spherical symmetry around the charge, and points outward. By considering the symmetry of the electric field, we choose a sphere S with an arbitrary radius r as a Gaussian surface where the point charge is in the center of the sphere. As a result of such a choice, the magnitude of the electric field E is constant over the Gaussian surface and the field is perpendicular to the sphere. Gauss's law states that the surface integral of the electric field E over the sphere S is equal to the charge Q enclosed by the sphere over epsilon naught. For the sphere S, the surface integral is given by the magnitude of the electric field E over the sphere, times the surface area S of the sphere, which is equal to 4 pi times the square of the radius r of the sphere. Then Q over epsilon naught is equal to 4 pi times r squared times E. If we express the magnitude E from this equation, we can see that the magnitude of the electric field is equal to 1 over 4 pi epsilon naught, times Q over r squared. Since we know that the field is spherically symmetric, we can conclude that the electric field E due to a point charge Q at the distance r from the point charge is given by 1 over 4 pi times epsilon naught, times Q over r squared, times the vector r by the distance r. Here the vector are points from the source charge q to an arbitrary point at the distance r. We already derived this formula for a point charge from Coulomb's law. We will obtain Coulomb's law from this formula, if we place a point charge q' at the distance r from the source charge q and determine the electrostatic force F acting on the charge q' in the electric field E. The magnitude of the force is given by q' times the magnitude of the electric field E at the distance r from the source charge q. If we substitute the result obtained from Gauss's law into this equation, the magnitude of the force can be written as 1 over 4 pi times epsilon naught, times q' times q over r squared. Since the electric field is spherically symmetric around the source charge q, that is the force exerted on the charge q' points radially outward from the charge q, we can state the following. The force F is equal to 1 over 4 pi times epsilon naught, times q' times q over r squared, times the vector r divided by its length, which is Coulomb's law. In the next example we apply Gauss's law to determine the electric field for a thin spherical shell of uniform surface charge. Here we can see a spherical shell S with the radius R, which has a uniform distribution of charge with the total amount of charge q. Due to the homogeneous distribution of charge over the shell, the electric field E is spherically symmetric, and the field lines point radially outward from the positively charged shell. If we examine the electric field outside the shell, we can choose a sphere S1 with a radius r greater than R as a Gaussian surface, which encloses the charged shell. For such a choice, the magnitude of the electric field is constant over the surface S1, and the field lines are perpendicular to the sphere. Here the integral of the electric field E due to the charged shell over the sphere S1 can be written as the magnitude E of the field over the Gaussian surface, times the surface area S1 of the sphere, where the area is equal to 4 pi times r squared. Since Gauss's law states that the surface integral is equal to the charge q enclosed by the sphere over epsilon naught, we can express the magnitude E from this equation. Then the magnitude E of the electric field outside the shell is equal to 1 over 4 pi times epsilon naught, times q over r squared. In order to study the electric field inside the shell, we choose a sphere S2 with the radius r smaller than R as a Gaussian surface. The surface integral of the electric field E over the sphere S2 is equal to the magnitude E of the field over the sphere, times the surface area S2 of the sphere, where the area is given by 4 pi times r squared. Gauss's law states that the surface integral over the sphere S2 is equal to the charge enclosed by the sphere over epsilon naught, but there is no charge inside the sphere. As a result, the surface integral vanishes and so does the electric field over the Gaussian surface. Since the radius of the sphere is less than the radius in the shell but otherwise arbitrary, the electric field must be zero inside the shell. Then we conclude that the electric field E due to a uniformly charged spherical shell with the total positive charge q is the following. In an arbitrary point outside the shell, it is given by 1 over 4 pi epsilon naught, times the charge q over the square of the distance r between the center of the shell and that point, times the vector r pointing from the center to that point divided by its length. Whereas the electric field vanishes inside the spherical shell. This formula also shows that the uniformly charged shell with the total charge q is equivalent to a point charge q placed in its center. In other words, the electric field outside the shell is the same as if the entire charge were concentrated at the center of the shell. Here we plot the magnitude of the electric field E as a function of the distance r from the center of the spherical shell S. The graph shows that there is no electric field inside the shell. That is, the magnitude of the field vanishes at distances from the center less than the radius R of the shell. Outside the shell, that is at distances greater than the radius R, the magnitude of the electric field follows the inverse square law, and it reaches its maximum value at the surface of the shell, which is equal to 1 over 4 pi epsilon naught, times q over the square of R. In the following example of the application of Gauss's law, we determine the electric field due to a uniformly distributed charge in a sphere. Here we can see a uniformly charged sphere S of the radius R with the total charge q. Due to the homogeneous distribution of the positive charge within the sphere, the electric field E is spherically symmetric both inside and outside the sphere, and the field lines point radially outward from its surface. For the sake of simplicity, we omitted the field lines inside the sphere. If we examine the electric field outside the sphere S, we can choose a sphere S1 with a radius r greater than R as a Gaussian surface, which encloses the charged sphere. For such a choice, the magnitude of the electric field is constant over the surface S1, and the field lines are perpendicular to the surface. Here the integral of the electric field E due to the charged sphere over the Gaussian surface S1 can be written as the magnitude E of the field over the surface, times the area S1 of the surface. This area is equal to 4 pi times r squared. Since Gauss's law states that the surface integral is equal to the charge q enclosed by the Gaussian surface over epsilon naught, we can express the magnitude E from this equation. Then the magnitude E of the electric field outside the sphere S is equal to 1 over 4 pi times epsilon naught, times q over r squared. In order to study the electric field inside the charged sphere S, we choose a sphere S2 with the radius r smaller than capital R as a Gaussian surface. The surface integral of the electric field E over the sphere S2 is equal to the magnitude E of the field over the Gaussian surface, times the area S2 of the surface, where the area is given by 4 pi times r squared. Gauss's law states that the surface integral over the sphere S2 is equal to the charge q prime enclosed by the sphere S2 over epsilon naught. Since the charge is uniformly distributed throughout the sphere S, the amount of charge enclosed by the sphere S2 is proportional to its volume. As a result, the charge enclosed by the sphere S2 bears the same proportion to the charge enclosed by the sphere S as the volume of the sphere S2 to the volume of the sphere S. The volume of a sphere is proportional to the cube of its radius, and we can write that the charge q prime enclosed by the sphere S2 is equal to the cube of the ratio of its radius r to the radius capital R of the sphere S, times the total charge q distributed within the sphere S. If we substitute this expression into the surface integral and express the magnitude E from the result, we obtain 1 over 4 pi times epsilon naught, times q over the cube of capital R, times r. Then we conclude that the electric field E for a uniformly charged spherical sphere of the radius capital R with the total positive charge q is the following. In an arbitrary point outside the sphere, it is given by 1 over 4 pi epsilon naught, times the charge q over the square of the distance r between the center of the sphere and that point, times the vector r pointing from the center to that point divided by its length. In an arbitrary point inside the sphere, the electric field E is equal to 1 over 4 pi times epsilon naught, times q over the cube of capital R, times the vector r. This formula also shows that the uniformly charged sphere with the total charge q is equivalent to a point charge q placed in its center. In other words, the electric field outside the sphere is the same as if the entire charge were concentrated at the center of the sphere. Here we plot the magnitude of the electric field E as a function of the distance r from the center of the sphere S. The graph shows that the magnitude of the electric field is directly proportional to the distance from the center inside the sphere, that is at distances from the center less than the radius capital R of the sphere. Outside the sphere, that is at distances greater than the radius capital R, the magnitude of the electric field follows the inverse square law and it reaches its maximum value at the surface of the sphere, which is equal to 1 over 4 pi epsilon naught, times q over the square of capital R. After having studied spherically symmetric electric fields, let us see how we can apply Gauss's law to determine the electric field for a uniformly charged infinite line, where the linear charge density lambda is constant along the line. We have already seen that the electric field for such a distribution of charge is cylindrical symmetric along the line. If the charge density lambda is positive, then the electric field E points radially outward from the line of charge. Therefore, we can choose a cylinder S with arbitrary radius r and the height or length L as a Gaussian surface such that its axis is along the charged line. For such a choice, the electric field lines are perpendicular to the curved surface of the cylinder and the magnitude of the electric field is constant over the surface. At the same time, the field lines are parallel with the two bases of the cylinder and do not intersect them. The electric flux through the cylinder is given by the surface integral of the electric field over the cylinder, which can be split into the integrals over the three parts of the cylinder, the curved surface and the two bases. Since the field lines do not intersect the bases, the flux through them vanishes. Then the integral of the electric field E over the Gaussian surface S reduces to the integral over its curved surface, which is equal to the magnitude E over the surface, times the area S of the surface. The area of the curved surface is given by the product of the circumference of the bases, times the height of the cylinder, that is 2 pi times r times L. As a result, the electric flux through the cylinder is equal to 2 pi times r times L times E. Gauss's law states that the electric flux through the Gaussian surface S is given by the charge q enclosed by the surface over epsilon naught. Here the charge q is equal to the linear charge density lambda times the length L. If we express the magnitude of the electric field E from this equation, we can write it as lambda over 2 pi times r times epsilon naught. Since the radius r of the Gaussian surface is arbitrary, we conclude that the electric field E at the distance r from a uniformly charged infinite line with the charge density lambda is given by 1 over 2 pi times epsilon naught, times lambda over r, times the vector r divided by its length. Here the vector r is perpendicular to the charged line and points from the line to any given point at the distance r from the line. This result also provides a good approximation for the electric field due to a uniformly charged thin wire with a finite length in the vicinity of the wire far from its ends. Here we plot the magnitude of the electric field E around the line as a function of a distance r from the line, and the graph demonstrates that the electric field strength is inversely proportional to the distance r. By applying Coulomb's law, we already obtained this formula for the magnitude of the electric field. However, we can see that it is easier to derive the same result if we use Gauss's law. In the next example, we apply Gauss's law to determine the electric field for a uniformly charged infinite plane, which we have already done by using Coulomb's law. When we considered such a plane with a constant surface charge density sigma, we saw that the electric field E has a reflection symmetry across the plane. The field is perpendicular to the plane and points outward from it. If the plane is positively charged, that is, sigma is positive. We can exploit this symmetry of the field if we choose a cylinder S with an arbitrary size as a Gaussian surface, which is cut in half by the plane and its bases are parallel with it. Then the electric field due to the uniform surface charge over the plane is perpendicular to the bases of the cylinder, and its magnitude is constant over them. At the same time, the electric field lines are parallel with the curved surface of the cylinder and do not pass through it. If we calculate the electric flux through the Gaussian surface S, we can split the integral of the electric field over the cylinder into the integrals over the curved surface and the bases of the cylinder, where only the surface integrals over the bases give contributions to the flux. Then the electric flux is equal to 2 times the magnitude of the electric field over the bases times the surface area S of the bases. Gauss's law states that the surface integral of the electric field E over the cylinder is equal to the charge Q enclosed by the cylinder over epsilon naught. The total charge Q enclosed by the cylinder is given by the surface charge density sigma, times the area S of the intersection of the plane and the cylinder. We can express east from this equation and see that the magnitude of the electric field around the uniformly charged infinite plane is given by its surface charge density sigma divided by 2 times epsilon naught. We have just demonstrated again that the electric field of such a charged plane is constant and does not depend on the distance from the plane. We also obtained this result by applying Coulomb's law, but this method using Gaussian surfaces adapted to the symmetry of the field is far more simple. Based on this result, we have already determined the electric field produced by 2 infinite parallel planes, which have opposite charges with the constant surface charge densities plus and minus sigma. The electric field E sub plus due to the positively charged plane is uniform with the magnitude of sigma over 2 times epsilon naught. The uniform electric field is perpendicular to the plane and points outward from it. The electric field E sub minus due to the negatively charged plane is also uniform and has the same magnitude, but points inward. When we applied the principle of superposition of electric fields, then we saw that the electric fields E sub plus and E sub minus cancel each other out outside the space between the planes, and the net electric field E is 0. We also saw that the 2 electric fields in the space between the planes point in the same direction, therefore their superposition gives the uniform electric field E with the magnitude of sigma over epsilon naught. The field between the plates points from the positively charged plane to the negatively charged one. This example demonstrates that the combination of Gauss's law and the principle of superposition of electric fields provides an efficient method to determine the electric field due to even more complicated distributions of charge, if the geometry of the field exhibits some symmetry. Let us summarize the main points of this presentation on electric field. In this presentation we introduce the concept of electric field, which describes the Coulomb interaction between charges or charged bodies. We assume that the electrostatic force acting on a charged body indicates the presence of electric field in empty space around the body, and the source of this field is another charged body or a set of charged bodies. We defined electric field strength so that we can give a quantitative description of electric fields based on the application of Coulomb's law. We also demonstrated that the principle of superposition holds for electric fields, that is, the net electric field of more electric fields due to different charged bodies is the vector sum of the individual fields. We saw that electric field lines provide a visual representation of the geometry, that is, the spatial distribution of electric fields. The direction of electric field is the tangent to the field lines at any point, and by convention, The number of the field lines per unit area at a given point in space is equal to the magnitude of the field strength at that point. We determined the electrostatic fields due to point charges, dipoles and continuous distributions of charge by applying Coulomb's law. We demonstrated that the electric field of a point charge is spherically symmetric around the charge and its strength is inversely proportional to the distance from the charge. In the case of a dipole, the geometry of the field is more complicated, but its magnitude along its axis and its transversal plane is inversely proportional to the cube of the distance. We also showed that the electric field has a cylindrical symmetry for a uniformly charged infinite line, and the magnitude of the field is inversely proportional to the distance from the line. We could determine the electric field along the axis of a uniformly charged circle or disk as well. In the case of a uniformly charged infinite plane, the electric field is reflection symmetric and uniform throughout the space, which allows us to create a uniform electric field confined in the space between two oppositely charged plates. We also examined the motion of charged particles and dipoles in electric fields by applying the laws of motion for the electrostatic force. We determined the equations of motion of electrons propagating in a uniform electric field. We saw that an electron has a motion similar to free fall, if it is placed in the uniform electric field accelerating the particle in the direction opposite to the field. If the initial velocity of the electron is perpendicular to the uniform electric field, it behaves like a horizontal projectile in a uniform gravitational field and performs a parabolic motion. Then we presented Millikan's oil drop experiment based on the principles of the motion of the charged particles in electric field. We described the apparatus constructed for the experiment and explained the measurement performed with the charged oil droplets in a uniform electric field. We saw that the balance of the forces acting in the oil droplets allowed Millikan to measure the charge of the droplets and determine the elementary electric charge. We also introduced the concept of electric flux, defined as the number of electric field lines per unit area, which describes the rate of flow of the electric field through a given area. We demonstrated that the electric flux through a surface is given by the integral of the electric field strength over the surface. Then we determined the electric flux through a closed surface for a point charge, and we saw that the net flux through the closed surface vanishes for a point charge outside the surface. By generalizing this result for an arbitrary distribution of charge, we proved Gauss's law, which establishes a relationship between the electric flux through a closed surface and the amount of electric charge enclosed by the surface. Since the law holds for a continuous distribution of charge, we could write Gauss's law in differential form, stating that the divergence of the electric field measures the intensity of the source charge of the field. We have also demonstrated that Gauss's law, together with the principle of superposition of electric fields, can be used to determine the electric field due to symmetric charge distributions, and provides a far more simple method than the application of Coulomb's law. This method enabled us to rederive results obtained for the electric fields due to a point charge and a uniformly charged infinite line and plane. At the same time, it also helped to determine the electric fields for a uniformly charged spherical shell and a uniformly charged sphere.